Okay guys, welcome to lecture 10. Today's topic is Shor's quantum factoring algorithm. This is the Introduction to Quantum Computing course, summer 2020 offering at the University of Paderborn. Just a quick announcement, the next assignment should be out soon, which means either today or tomorrow, roughly speaking. Today's topic is easily one of the most important results to come out of the field of quantum computation. You know, the quote at the top of the lecture is by Eric Temple-Bell, so let me start with that as usual. It reads, Euclid taught me that without assumptions, there is no proof. Therefore, in any argument, examine the assumptions. Okay, and quantum computers breaking crypto systems like RSA is going to be an example of this, basically. So basically, we saw last lecture how to use the quantum Fourier transform to implement something called quantum phase estimation. And once we have quantum phase estimation, we're in principle ready, basically, to derive the quantum factoring algorithm. So just a bit of history. So the factoring algorithm was discovered in 1994 by Peter Shor. And what this basically did is, in some sense, it forced the classical computer science community to really reevaluate one of its core assumptions. Okay, so which assumption are we talking about? Well, essentially at that time, the problem of factorizing large integers, basically, so if I give you a large integer n, can you factorize it into its prime factors? That problem was believed to be hard for a classical computer. Okay, and in 1978, Revest, Shamir, and Edelman came up with a crypto system or a cryptographic scheme, commonly now known as RSA after the founders, which basically remains widely used in practice, right? It's used to basically secure data online. Okay, and RSA had been presumed secure basically since its inception because people believed factoring was hard. Okay, but I mean, let's be clear that even in just looking at, of course, the algorithm makes it clear. The RSA algorithm makes it clear that factoring will break this thing. But even in the abstract of the paper, it was very clear what the assumption is. It read, here's a quote from the abstract. The security of the system rests in part on the difficulty of factoring the published divisor n. Okay, so in some sense, it's an Achilles heel that's hiding in plain sight, if you will, right? And so, lo and behold, in 1994, Peter Shor comes along and says, aha, well, you guys have been assuming that this problem is hard for, almost 2 decades now, but, here's a quantum algorithm that can break the factoring problem and hence can break this very popular crypto system RSA. Okay, so that's why we're going to talk about the factoring algorithm, and that's roughly why it's so important. So in this lecture, of course, we'll talk about the algorithm, and at the very end, I'll briefly go over, how you use it to break RSA. Okay, and in particular, that means reviewing RSA very quickly. The factoring algorithm itself, it can be thought of as having kind of 3 steps. The first step is you're going to not actually solve factoring. You're going to first reduce factoring to something called order finding, and then you're going to solve order finding. And order finding, to solve that, we're going to need 2 things. We're going to do a sampling step using the quantum phase estimation, and then we'll have a classical post-processing step using something called the continued fractions algorithm. So before you're doing any of this, however, okay, we're computer scientists. That means we like to be formal about things. We should start by formally defining what we mean about the integer factorization problem, and we should understand the complexity theoretic context of this problem, okay, before we talk about any sort of algorithm for it. Okay, so section 2 of the notes is just basically the integer factorization algorithm. Okay. Okay. So as you guys probably all remember from your math classes, basically in university, the fundamental theorem of arithmetic says that if I give you any composite number n, right, some integer, I could always decompose it into its prime factors, right? So p1 to some power k1, p2 to some power k2, pm to some km. So this is for all positive integers n. Okay, so maybe I'll write z plus to denote positive integers. We can always write n this way, right? And each of these pi's, these are all primes. Okay, and of course you have some multiplicity for each prime in general. Each prime can, of course, appear more than once. Okay, and of course each pi is going to be distinct, otherwise I'd write them together. And this decomposition is, of course, unique. So intuitively, the factoring problem is going to be, I'm going to give you n, and I'm going to ask for the prime factors. Okay, so before I go any further, let's first do the first exercise in the notes. And now, by the way, we've started a numbering exercise in the notes. Woohoo! Okay, so now I can refer to exercise 1, right? So exercise 1 in the notes is something everybody should do the first time they stare at this problem to convince themselves that really the naive algorithm for this problem is not polynomial time, okay? So consider this naive algorithm. This is exercise 1. So the naive algorithm is you basically write a for loop. And what you do is you go from, say, I equals to, say, 2, all the way up to, say, roughly the square root of n. And then you just check if I divides n. Okay, and so you basically try all the factors via brute force from 2 up to square root n. And then whenever you find a factor, you just return it, right? Roughly speaking, okay? And, this algorithm, roughly speaking, let's just say you're looking for one factor, not all of them. This will take at most order square root n field operations over the integers or the real numbers, right? I mean, you're going to, every time you do one division, it'll be one field operation. So why is this not polynomial time? Because it looks like it's, scaling with n, basically, right? And the key point is that, so here's the question, why is this naive algorithm not a polynomial time? Okay, so I highly encourage you to pause this video right now and think about this for a second. And the hint is going to be that you need to think about the encoding size of the input n. Okay? Okay, so if you haven't paused the video, or if you restart it, let me give you the answer. Basically, the answer is that the encoding size of the input is going to be what? If I want to write the integer n, I don't write out n bits, right? I write out log n bits. So it's order log n, right? That's, if I feed this thing into a Turing machine, that's how I specify n in binary. And so a runtime, a poly runtime, remember we say polynomial always in the size of the input, means something that's going to scale like poly log n. Okay, that's what we would consider efficient. But of course, this thing over here is not poly log n, it scales with n basically, right? Square root of n. So that's why this thing is not efficient. Okay, if you didn't understand that yet, I would certainly encourage, again, pausing the video, going back and thinking about it some more, because I think it's crucial to understand that before you move forward. Okay, so this is exercise 1. This is why the very naive algorithm you probably think of first just doesn't work. Okay, so now I'm going to formalize what I mean by factoring. So I gave you kind of a hand-wavy definition, but again, we're theoretical computer scientists. We want to be very formal. And we like to think about decision problems in particular. Okay, so that means that we like yes or no answers. Okay, or questions with yes or no answers, because that's how we define complexity classes like P and NP, right? They're always defined in terms of yes or no questions. Okay, so the way we're going to do this is definition 3 in the notes. And I'm going to henceforth just call this problem factor in capital letters. The input is going to be a positive integer capital N greater than 1. And you'll also get some threshold parameter. Let's say it's capital K, and it's also a positive integer. And the output is, whoops, does n have a prime factor smaller than k? Okay, so all I'm doing is I'm turning this into a yes or no question, right? I mean, so I have to give you a threshold. Is the prime factor smaller than k or not? You can, is there a prime factor smaller than k? And any sort of optimization problem, typically you can also turn it into a decision problem using this sort of threshold trick. So this is very general. And exercise 4 in the notes shows that without loss of generality, if you want to compute all the factors, it suffices to be able to solve this decision problem, right? So why is that? Well, if you want to figure out, say, the smallest factor of n, what do you do? Well, you could use this threshold to do binary search, right? To figure out, to zoom in on the right factor very, very quickly in the log of n iterations, basically. And once you have one factor, you just divide it out and you remove it, and then you repeat the entire process over again to find the remaining factors. Okay? So, it's without loss generality in some sense that we talk about decision problems, because typically you can solve the optimization version given the ability to solve the decision version. Okay, so that's the formal definition of factoring. Let's think a little bit about where this thing lives in terms of complexity land. Okay. So complexity theoretic considerations. Okay, so what's not known, obviously, is that factors in P. So remember, P is the complexity class of problems or languages that can be decided using a polynomial time Turing machine. So that's not known, but it's also not known that factor is NP complete. Okay, so remember, these are the set of problems that can be reduced to any other problem in NP, such as 3-sat is the canonical one. And so we also don't know that, factor is rigorously hard in some sense. Okay. Now, the funny thing, however, is that there's a problem that's very closely related to factor. Looks almost, this problem is the primality testing problem. Okay. But, so there's a big but. Okay, the primality testing problem is NP. Okay, so this was a breakthrough result that I think was in the early 2000s, that the following problem, and let me just formalize the problem first. So you're given, again, a capital N in the positive integers, just like for factoring. You just want to know, is n composite? Okay, by which I mean, is it the product of more than one prime? Okay, more than one non-trivial prime. Okay, and even though this sounds extremely similar to factoring, right? It's the same kind of idea. Certainly, if you can factor, then you can answer this problem, right? Primality testing is in P. Okay, and again, this was a breakthrough result. This happened in, I think, early 2000s. But let me be clear also that the breakthrough was to make the algorithm deterministic. Before that, there had long been known a randomized algorithm for primality testing that essentially worked for all the input instances you can care to solve, essentially, right? So interestingly, this closely related problem is in P, but we don't know what to say about factoring. Now, what we can say as a result, however, because primality testing is in P, a consequence of this is that one can show that factor is in both NP intersect co-NP. Okay, so remember that very briefly, for NP, whenever you have a yes instance, then that means that, there exists a proof you could feed to a verifier to accept. Okay, and so I'm going to assume a little bit of basic complexity theoretic background here in terms of P and NP. And remember that co-NP is basically the opposite of this, in the sense that in the yes case, for all proofs, the verifier, well, okay, formally speaking, you might define it as accepts or rejects. I mean, it doesn't really matter in some sense. Okay, so this is kind of the difference, right? So in some sense, yes instances can be proven NP, and no instances can be proven in co-NP. Okay. So factor would fall into both complexity classes. So why is this true? This is exercise 5 and 6. And so basically, why is factor in NP? Well, if factor, the number n has a prime factor smaller than k, remember that's how I defined it, right? Then it's very easy to prove to me, right? You just give me that prime factor, right? So you just give me the prime factor, which is less than or equal to k, right? And then I could just divide n by that prime factor, and I can check that indeed it's a factor. Okay. And of course, what you gave me, I could also check that it's a prime factor because I have a primality testing algorithm, right? Here it is. So I could also verify that. And how about this thing? How do you prove that this thing is in co-NP? Well, basically what you need is that when there is no prime factor smaller than k, you should be able to prove this to me, right? So for all proofs you give me, the verifier will, accept or reject, however you want to define that criteria, right? But it's going to do the same thing on all proofs. So in particular, if this thing does not have a prime smaller than k, you need to be able to prove it to me. And well, how do you do that? Well, you just give me the prime factorization, the full prime factorization. Okay. And with a bit of thought, you could see that this doesn't take a lot of space to write down. You'll never have more than order polylog n prime factors, basically. Not including multiplicities. Well, I guess even including multiplicities. And so if you were to give me the full prime factorization, and I can check indeed, the factors you give me are prime, because again, I have a primality testing algorithm, then I can verify myself that indeed, there is no prime factor smaller than k. Okay, so factors in this sense, it's in both these complexity classes. Whether there is a small factor or not, in both cases, you can prove it to me. Okay? And now there's a big but, which is that, with a bit of thought, you can show, and we won't do this here. So if we have a language such as factor that happens to be in both NP and co-NP, and it's NP complete, or say co-NP complete, doesn't really matter. Then it would imply that NP equals to co-NP. Okay, so, we said earlier that we don't know that factoring is NP complete. But this is basically saying that because we know that factor is in NP and co-NP, if it were to be NP complete, then there would be a pretty strong consequence to this. The consequence would be that NP would equal to co-NP. And again, this is something you can prove. I'm not proving it here. And this consequence, NP equals to co-NP, again, you can prove this, but I'm not going to because I don't want to introduce more definitions here. This implies that something called the polynomial time hierarchy, okay, if you haven't seen this before, I certainly recommend you take a moment to pause this video and go look it up on Wiki. This thing would collapse. Okay? And so that collapse is, more or less deemed, just as unlikely as P equaling to NP. It's really strongly believed to be a highly unlikely consequence for this pH to collapse. So in a nutshell, what this is basically saying is that it's highly unlikely that a factor is going to be NP complete. Okay, so it's not necessarily known to be NP, but it's also not known to be NP complete, and moreover, we don't think it's NP complete. Okay, so this might sound very, very dissatisfying or unsatisfying. I really should know which of those two is the correct word to use. But there is kind of a silver lining, and the silver lining is that there is such a thing as NP intermediate problems. Okay? And in particular, what Ladner proved, I think this is 1975, right? What he proved is that if P is not equal to NP, okay, then there exist these so-called intermediate problems, which are, there are languages L such that L is neither in P and L is not NP complete. Okay, so that's kind of amazing, right? This is basically saying that, there's a kind of a complexity class or something that's sandwiched in between things that are polynomial time solvable and things that are not necessarily polynomial time solvable, but they don't capture the difficulty of all of NP. And, Ladner's construction is arguably quite artificial, but, it works for what it's supposed to work for. Ideally, you want natural problems, which are NP intermediate, and there are very, very few of those. And factoring is one of the few known natural NP intermediate problems. Okay, so that's something nice that comes out of this. Okay, so it's not polynomial time solvable as far as we know, but we also strongly disbelieve that it's NP complete. Okay, So, for all intents and purposes, we probably believe this problem is NP intermediate. Let me just say a little bit about, and I don't think you can get away with talking about the factoring algorithm without talking about the extended Church-Turing thesis briefly. Okay, and so you've probably seen the regular Church-Turing thesis in your Introduction to Languages and Automata courses. So remember that the Church-Turing thesis is basically the backbone on which most of theoretical computer science rests, right? And in particular, the Church-Turing thesis basically says that Turing machines capture everything there is to know about computation, in the sense that Turing machines can simulate, in quotes, any other model of computation. Okay, so that's very roughly what the Church-Turing thesis states. Okay, so we might as well just solve Turing machines, and that tells us everything we need to know. But there is a slightly different version, an extended version. Okay, and then the extended Church-Turing thesis. All right, and this looks almost the same. So, I'll put these guys, except we're going to insert one word here. We're going to insert the word efficiently. Okay, and the other thing we're going to do for the extended Church-Turing thesis is here we're going to say that the model of computation should be physically realizable. Okay, so we want to talk about, we want to posit that, and let's be clear, of course, both of these theses are theses. They're not proven facts. It's not clear at all how you'd even begin to prove this thing. Okay, but if we're going to demand on top of this that Turing machines can efficiently simulate other models of computation, then, it's very reasonable to ask that the model of computation at least be physically realizable, right? Our laws of physics should allow this model to be actually built on a large scale, okay? Otherwise, obviously, who cares if you can efficiently simulate it or not? Okay, so these terms in red are basically what you add to the regular thesis to get the extended version of the thesis. And let me be clear that, the extended version of the thesis is much less commonly accepted than the standard Church-Turing thesis, which is, very broadly accepted, okay? So there's a sense in which it was the discovery of Shor's factoring algorithm which kind of made the extended version more quote-unquote popular. Not in the sense of people believing it, but necessarily, but just gave it more visibility. Okay, so the point is that because we have these added constraints of efficiency and physical realizability, when you'll see now that Shor's factoring algorithm and the extended Church-Turing thesis basically clash. And what we've learned is that, assuming Shor's factoring algorithm is correct, which I think everybody agrees, we're now at a crossroads in theoretical TCS, theoretical computer science. Okay, so one of the following is false. Okay, so I'm going to write down three statements, and one of the following must be incorrect. Okay, so the first statement is that the extended Church-Turing thesis is true. Okay, so that's the first statement. The second statement is that factor or factoring does not have an efficient classical algorithm. So this is basically what most of the classical community believes. Okay, so factor is not NP. And the third statement is what the quantum community believes, which is that, for the most part at least, which is that large-scale quantum computers can be built. Okay? So one of these three statements has to be false. Okay, so let's just do an example of this, right? If the Church-Turing thesis is true, and you can build large-scale quantum computers, well, what that tells you basically, what that tells you basically is that because the Church-Turing thesis, the extended version, says that any classical computer can simulate a quantum one efficiently, and because quantum computers are realizable, you can build them basically, then that means that there must also be a classical algorithm for factoring, right? We just haven't found it yet. Okay. Of course, if factoring doesn't have an efficient classical algorithm, and we can build large-scale quantum computers, then the extended Church-Turing thesis is false. Okay. And finally, the other interesting direction is that, well, if the extended Church-Turing thesis is true, and factoring does not have an efficient classical algorithm, well, that means that somehow you shouldn't be able to do factoring quantumly, right? And so mathematically you can do it. So the only other logical conclusion is that we must fail this criterion, right? That the model must not be physically realizable on a large scale. Okay. So it's really interesting. It's very exciting. One of these things, some of which are arguably more strongly believed than others. I'd probably argue that 2 and 3 are the most strongly believed out of and 1 is the least strongly believed. But one of them must be false. Okay, so this is all I want to say about formalizing factoring as a decision problem. In terms of its complexity theory, that we don't necessarily believe it's NP, and we certainly don't believe it to be NP complete, because it would collapse the polynomial time hierarchy. It's believed to be NP intermediate. And finally, it leads to this very nice crossroads in which one of these statements I've written down must be false on the screen. Okay, so now we can talk about the actual factoring algorithm. Okay, so this is section 3. And again, this proceeds basically in 3 high-level steps. First, we're not going to solve factoring. We're actually going to reduce factoring to order finding. So I have to define that and show you the reduction. So we're going to do that first. And then once we have reduced to order finding, we can solve order finding by combining quantum phase estimation and something called the continued fractions algorithm. So let's start with the reduction, reducing factor to order finding. Okay, section 3.1 in the notes. So let me define order finding. Okay, and the acronym I'll use is just capital order. So for this, you're going to have to think back to kind of like your basic modular arithmetic that you probably learned in one of your first years in your university degree. And what it says is the following. Input output, right? So what you give me are positive integers, n, okay? And some x that's between 1 but strictly smaller than n. And x is coprime to n. Okay, so coprime to n means that, remember this means that x and n, if you write them both in their prime factorization, they will not share any prime factors. Okay, so so they share no prime factors, and hence no factors in general, right? Okay, so that's just a definition just to refresh your memory. Okay, and what is the output? So the output is the smallest positive. Oh, what happened there? Okay, well, we'll just keep going. The least positive integer r. And so this is going to be called the order. That's why it's called order finding. You're trying to find the order. That satisfies x to the r is equivalent to 1 modulo n. Okay, so remember this just means that if I take the left side of this thing and I divide through by n, the remainder I get is 1. And, it's always good to remind yourself what is the equivalent definition of this equation, modulo n, right? That just means that x to the r is equal to, some number, let's call it alpha times n, so some multiple of n, right? So this is an integer, right? Plus 1. So if you want to express x to the r, it's just some integer times n, right? That part disappears when you divide by n, and then you have the remainder 1. So it's always good to keep that alternate definition in your mind when you think about modular arithmetic. So this is the order finding problem, and the claim is that if you can solve order finding, then you can solve factoring. And that's what we're going to show now. Note that, by the way, I did not write this as a decision problem like I did factor, just to keep things a bit simpler, one less parameter floating around. Because I just said, give me the smallest positive integer r. Of course, you could turn this into a decision problem just like we did for factor. Okay, so just some brief terminology that we're going to need. So we already reviewed what coprime means. GCD, greatest common divisor, basically, is the greatest common divisor of x and y. Okay, and these are natural numbers, so just what's the biggest number that basically divides both of these two? Okay, and now I could be slightly more formal. When I say x is coprime to y, that's equivalent to saying that the GCD of x and y is 1. Right? The biggest number that divides them both is just 1. There are no other non-trivial factors. Okay, so to reduce factoring to order finding, we're basically going to start at almost a trivial exercise. Okay, and so this is exercise 10. I'll sort of sketch it here. But basically, this is going to give away our strategy. Okay? So the claim is that let x be a non-trivial solution to x minus 1. So I'm going to write down an equation. A constraint basically is equivalent to 0 mod n. Okay, so find me an x that satisfies this. And non-trivial, what do I mean by non-trivial, right? I mean, it's kind of trivial to solve this, right? I could just plug in x equal to 1 or x equal to minus 1. So that means that x is not in 1 or minus 1 mod n. Okay. So suppose I have some non-trivial solution to this equation. And then basically GCD of x minus 1 and n, or the greatest common divisor x plus 1. So these are the two terms you see here, right? Here's one, here's the other. Is a factor, a non-trivial factor of n. Okay. Okay, so why is this true? Right, I mean, because obviously what we're looking for is n, right? Sorry, a factor of n. And so this gives us a kind of a first way to make a step towards that. And so how do we do this? Well, what we're saying is that, n, of course, what does this mean? This equation says that n divides, basically, this product, x minus 1 times x plus 1. That's what the equation says. Okay, there's no remainder. And so there are three possible ways this could happen, right? Either n fully divides x minus 1, right? It goes into that bracket, or it divides x plus 1, okay? Or n doesn't divide either of the brackets, but the prime factors of n kind of split up, and some of them will divide this bracket, some of them will divide this bracket, right? Those are the only ways this could work. And the first two paths I told you are actually impossible, right? Because we're asking for a non-trivial solution, right? So we assumed that, so note that we assumed a non-trivial solution, which for example means that we don't want x to be equivalent to 1 mod n. And of course this is the same thing as saying that it's not true that x minus 1 is equivalent to 0 mod n. Okay? Or in other words, we're assuming a non-trivial solution means that n does not divide x minus 1. Okay? So it just doesn't divide this, and it also doesn't divide this. That's the other assumption. And therefore, the only way this division could happen is that the prime factors of n, if, for example, if n is equal to p times q, for example, right? Then, as we'll see for, RSA, then the only conclusion is that, p, let's say, must divide x minus 1, and q must divide x plus 1, okay, or the other way around. Okay, that's the only other way this division could work. Okay, so that's why basically, and that's basically what this is saying. This GCD basically of x minus 1 and n would return the prime factor of n that goes into x minus 1 in this case. Okay, so this is very briefly the intuition as to why this exercise holds. Okay, why the claim holds. Okay, so all this is saying is that, let me rewrite this in a nice way, in a nicer way. So this equation, this is just a difference of squares, right? This is just the same as the equation x squared is equivalent to 1 mod n. Okay, that's all that is. And so what we conclude from this exercise is that finding a non-trivial solution x satisfying this thing allows us to factor n, or to more accurately to procure at least one factor of n. Well, I suppose if you have more than one factor, if you have multiple factors, the GCD of x minus 1 and n might not itself be prime, but you can recursively keep applying this at this point. Okay, but in our case, certainly for RSA, n is always going to be a product of two primes, so the GCD will always return for either P or QT. Okay, so it allows us to factor n. That's the first thing we take out of this. Okay, so now we can kind of forget about factoring, and now we're going to say, fixing n, which is going to be our composite number we want to factor. How do we find a non-trivial x satisfying this equation? Okay, and this sounds very complicated, but it turns out like the simplest possible idea works, which is that. So the question is, how to find x, and here it pays off to be really stupid. And by that I mean all you have to do is pick a random x that in addition has to be co-prime to n. So the answer is pick uniformly at random x and here I want to start introducing some notation. So whenever I write down Zn, I'm referring to the set 0, basically the numbers mod, I'm referring to the numbers mod n, the integers mod n, and so you're talking about this set, 0 up to n minus 1. So pick an x uniformly at random from Zn, okay? And additionally, we need x to be coprime to n, right? Because n is not necessarily prime. In our case, n is a composite number, p times q. So we need this additional restriction. Okay, and it turns out that when you do this with high probability, if you can extract the order of R from X, when you pick this X uniformly at random, its order allows you to construct a solution to X squared is equivalent to 1 mod n in a non-trivial fashion. Okay, so basically, to review, pick a random X coprime to n, compute its order, and its order will allow you to solve this equation, X squared is equivalent to 1 mod n. Now, I need to be more clear than that, of course. That's just the high-level view. So let's give some of the intuition. Okay, so maybe just intuition here. Okay, so this is exercise 12. Okay, so let's suppose let R be, and here I'm going to stress that R needs to be even, integer satisfying, x to the R is equivalent to 1 mod n. Okay. And so this is supposed to give you a little bit of the intuition as to why if you can find the order of an element x, then you can use it to find a solution to x squared is equivalent to 1 mod n. Okay, so how do we do that? Well, let's assume we had some way of computing, finding an x who has an order R which is even, basically, so that's what this is saying. And suppose we can compute the order R, right, for which later we're going to need the quantum algorithm. We don't know how to do that classically. Well then, the question is, you want to come up with, give a y satisfying y squared is equivalent to 1 mod n. Okay, so in other words, give me a y which satisfies this equation up here. Okay, so how do you do this? The obvious thing is this, right? If you think about it just a little bit, the obvious solution is that, since x to the R is equivalent to 1 mod n, all right, then certainly, x to the r over 2 times x to the r over 2, right, if you just take the square root essentially, is also equivalent to 1 mod n. And so let's just define y to be equal to this, right? It's just x to the r over 2. Okay, so if I can find, an x with an even order, and I can figure out the order itself, then I could immediately kind of write down what y should be, x to the r over 2, right? And then I'll know for sure that it'll satisfy this equation, x squared is equivalent, or y squared is equivalent to 1 mod n. Now, of course, this is not enough because remember we said we want to find x first of all. Not obvious how to do that, right? So we're going to randomly sample. We're going to cross our fingers and hope that that x has an even order, number 1. And number 2, it's not enough just for y to satisfy this, right? We also needed y to be a non-trivial solution to this equation, right? We didn't want the trivial solutions. So we have to argue now that random sampling allows us to find an x with high probability, which has an even order, and so that the square root of x to the r, this thing over here, that thing is not going to be a trivial solution to this. It will be a non-trivial solution to this equation. Okay, and so that leads us into the next kind of heading, which says, how do you find a non-trivial solution to x squared is equivalent to 1 mod n. Okay, so for this we're going to have to take a little bit of a detour into number theory, and I think it's worth seeing some of these facts again, because again, you've probably seen these at some point, but the last time, for example, I learned about the Chinese remainder theorem was, aside from Shor's factoring algorithm, of course, it was I think first year of undergrad at the University of Waterloo. I mean, so it had been a long time since I'd seen it. So I think it's a good idea to make sure to write these facts and just to refresh your memory of them. And maybe some of these you haven't seen before. But basically, to prove what we need to prove, we need 3 facts. And I'm going to write them down as facts 14, 15, and 16 in the notes. The first one is Fermat's little theorem. And I'm just going to abbreviate this for Theorem. It's funny how when you spell things wrong, it's almost like your brain has a spasm for a second when it sees it, like a spidey sense. Anyway, Fermat's little theorem, right, is the first one I'm going to write down. The second fact I'm going to write down, fact 15, is the Chinese remainder theorem. Okay, and abbreviated just CRT here. And finally, the last fact, which is, out of all the facts, perhaps the one you may or may not be familiar with is, and I'm just going to write it as the multiplicative group ZP is cyclic. And if you don't understand what those words mean, don't worry. In theory, there's group theory that's underlying all of this, but nothing of what I'll talk about will really mention the words group theory, and you don't really need to know it to prove some of these basic facts, basically. Okay. So again, as the quote atop last lecture by John von Neumann said, a lot of mathematics is not, it's not really understanding the math. And there's a sense in which you never really understand it. It's more, you just have to get used to it, right? And so, again, with group theory is another example where once you get used to it, it makes sense. But even without really knowing the formal words group theory, you can make sense of a lot of this just by thinking of it long enough. Okay. So let's start with Fermat's little theorem. It says, for any prime p and integer a to the p is equivalent again to a mod p. Okay, and moreover, and the version we'll be using here, if the prime does not, whoops, let me not use that notation. I'm also trying not to use division notation. If p does not divide a, so then you can say something even more, which is that a to the power p minus 1 is actually equivalent to 1 mod p. Okay, so this is the version we're going to use. So, if you give me an integer a and a prime p so that p does not divide through a, then this equality to 1 holds. Okay, so that's Fermat's little theorem. Let's state the Chinese remainder theorem. So this basically says that, maybe I'll start writing it here. So let's start with a set of integers larger than 1. So I give you a set of integers m1 through mn, be integers greater than 1. Okay, and each pair of which is coprime. Okay, so what that basically means that if I take any mi and mj from this list that are distinct, then they're both coprime. Their GCD is 1. Okay, then for any other set of integers you could give me, a1 through an, the following linear system. So I'm going to write down a system of equations, and the claim is going to be that this system will always have a solution. So we have x is equivalent to, so all of these are the same on the left, right? Okay, I'm going to write down a system of equations. So the first thing, let's fix the moduli. So those are the m1, m2 that you started with, right? These are these bad boys over here, right? And so the other thing I need are, what should x be equivalent to mod each of these moduli, which are coprime. And then there we're going to write, a1, a2, up to an. Okay, and so you should think of it this way, that, you should think of these moduli as being just fixed, and what's kind of a variable here is, what is the equivalence, right? What is the sequence of numbers you write down here in terms of the moduli? And what this is basically saying is that always has a solution. Okay, so in other words, if we fix the moduli, no matter what sequence of integers a1 through an you write down, basically, there's always some x which will satisfy all these equations simultaneously. Okay, and also x, how did I want to write this? Basically, all the solutions are equivalent modulo the product of the prime. So let me more, there are multiple solutions, but there is a unique such x, which is in the range 0, ... up to m, which is just the product of these moduli. Okay, let's see if I could move this thing because it's getting in my way and I'm not very happy. It's not good to be unhappy with these things, right? We will do what we can to fix it. No. Oh, maybe I need to use my mouse. Is that right? Hey, no, not good. All right, well, maybe I'll do. Why is it not? All right, maybe we'll just leave it for now. Okay. Okay, so that's the Chinese remainder theorem, right? And basically it just says this, that intuitively, is this an exercise here? So, okay, intuitively what the Chinese remainder theorem is going to buy us is that, instead of talking about, x mod capital M, right, we can instead talk about, each of these integers, a1 through an, mod each of these moduli, right? You can kind of switch back and forth between the so-called global view, which is mod capital M, and the local view, which is, mod each of these little m1 through mn. Okay, and it'll turn out that there's a bijection between these two sets. They're completely, you can always map between any a1 through an to some unique x and vice versa. Okay, and the last fact I'm going to give you, this multiplicative group, maybe I'll just put some underlines to kind of separate these things just a little bit. Probably should have left a little bit more space. So this fact, what it basically says is the following. It says that fix any positive prime P. Okay. Then there exists a so-called generator. Okay, just a fancy name. In the set ZP. Okay, so remember this is going to be the integers from 0 up to p minus 1. So there's some integer in that range, basically, such that any non-zero element E, which is also in that set, can be written G to the K is equivalent to E mod ZP. Okay, and this is, for some K, and K is also, well, K is in this range, again, is non-zero. Okay. So what this is basically saying is that, in fancy terminology, this just says that if P is a prime, then this, ZP is basically going to be a cyclic group. What does that mean in, plain language? It just basically means that as long as we're talking about the numbers 0 up to p minus 1 for P being a prime, if you want any number in that set, let's just call it E, you could always generate that number equivalently. Instead of writing the number down, there's some magical version of G, which is, for any P, there's some fixed choice of G. Okay, so you tell me P and I fix G. And whenever you pick an E now, any other element, you can always generate it just by raising G to a sufficiently high power. Okay, so that's why G is called a generator. It just generates this entire set, basically, or from 1 up to p minus 1, just by taking higher and higher powers. Okay. And so one thing I want to mention is that, by combining, this fact here, this generator fact, with Fermat's little theorem, in exercise 17, basically. So if you combining this with Fermat's little theorem, right? Maybe I'll try and keep that on the page for a second. Yeah. So if you combine this with Fermat's little theorem, what it basically says is that there exists a bijection, okay, a one-to-one onto map, basically, between elements E and powers K. Okay, so when I say powers K here, I'm talking about this K over here, right? And E is referring to this E. Okay. So, what this basically just says is that, I can think of picking a random element of ZP in two equivalent ways, right? One way is I could just pick a random element, E, but equivalently, remember G is fixed, conditioned on the choice of P, so equivalently, instead of picking E, I can instead just pick a uniformly random K in this range. And, for any fixed K, there's a unique E and vice versa. So, whether I randomly sample E's or K's, it doesn't matter. It's completely equivalent. Okay? Okay, so this implies that randomly sampling E is equivalent to random sampling K. Okay, there's a one-to-one onto correspondence. Okay, so here, these are just a bunch of facts. Let's just do a quick exercise so that we're just a little bit comfortable with this order stuff. So this is not a fact, but it will get used, this idea in this proof will get used. So I do put it here, and so make sure you understand both of these exercises before you continue. I think it's good to do exercise 17 and 18. So pause the video and do them. So this just basically says that let R be the order of X mod n. Okay. And let's consider some R prime bigger than R, right? That also satisfies this type of equation, right? X to the R prime, just like X to the R, is equivalent to 1 mod n. Okay. And the claim is that R prime divides R. Okay, so if I have any number bigger than R that also satisfies this type of equation, then it's always true that R prime is just some multiple of the actual order R. So i.e., R prime just equals to some alpha times R, right? For some integer, let's say, positive integer alpha. Okay. So why is this true? Well, let's just look at, here's a proof sketch. And again, the point of this is just to do a bit of practice with this before we get into some more serious proofs, right? Well, what is x to the r prime, right? Well, I know that, well, if I have x to the r prime mod n, basically, whatever that equals to, right? We know it equals 1, of course. I know that x to the r is equivalent to 1 mod n, right? And I know that and r is strictly smaller than r prime, right? So what I could always do is I could always rewrite this as, x to the r times x to the r prime minus r, right? Just trivially, right? I didn't do anything interesting. Mod n, right? But this I know is equivalent to 1, right? Here it is, right? I assume this fact up here, well, technically up here, right? So this now implies that x to the r prime minus r is also is also equivalent to 1 mod n, right? Because well, this was equivalent to 1 mod n, and all I did is I just kind of canceled off some redundant part on the left. So maybe I could add this in, right? And now you can just keep repeating this, right? You can keep subtracting off copies of r, right? And what's going to happen is eventually, either the exponent will go to 0, of course, in which case you perfectly divided through r prime with r, meaning, indeed, r prime was a multiple of r, or you're going to end up with an exponent which is strictly smaller than r, the order, right? And at that point, you're going to have something like, you have x to the, let's call it r double prime, whatever that is, right, is equivalent to 1 mod n, right? And such that r double prime is strictly smaller than r, right? You can't remove any more copies of r. And now you have a contradiction, right? Because r was supposed to be the smallest choice of exponent, basically, which caused this quantity on the left to go to 1, right? That causes x to go to 1. So r prime cannot be both equivalent to 1 and smaller than r, right? That's a contradiction. So this is a contradiction unless r double prime equals to 0. Okay, and so since r is the smallest smallest integer, I should say, satisfying x to the r is equivalent to 1 mod n. Okay. So that's, it's going to be useful to use this kind of proof idea that, we can, if I know something is equivalent to 1 mod n, I can kind of keep dividing out of the left side. Okay, and this also gives us just some practice with playing with modular arithmetic. Okay, so that's just all set up. We defined Fermat's little theorem. We defined the Chinese remainder theorem. We talked about the multiplicative, well, we talked about that in ZP, for P being prime, any element of the group can always be written as, some generator to some power. Okay, and now we're going to use all these to prove kind of the main theorem of the section, which is the following. The main theorem of the section, just keeping an eye on time here, is Theorem 19. Okay, so let me just write out the theorem. So let n be an odd composite natural number or positive integer. Okay, so obviously it's got to be odd because if it's even, it's trivial to factor this thing. You just pull out the factor 2. Okay, so let's define now. We've been talking about Zn, which is all the numbers from 0 up to n minus 1, basically. So let's define Zn star, which is, a subset of that. So instead of listing all the numbers, I'm just going to worry about the numbers. So all the numbers in Zn, okay, such that x additionally has to be coprime to n. Okay, so you share no common factors with n. So it's all the numbers between 0 and n minus 1, which share no common factors with n. Okay, so in particular, think about this for a second. So note, as a sanity check, is 0 question mark in Zn star? Okay, it's certainly in Zn, right? So why is it not in Zn star? Well, clearly 0 is not co-prime to n because, well, n factors 0, right? So 0 divided by n is 0. I mean, it goes through evenly in some sense. Okay. Good, so let's keep going. So remember the goal was, so why am I writing down this definition of Zn star? Remember we said that to pick this magical x that allowed us to solve this equation x squared is equivalent to 1 mod n, the key was we were just going to randomly sample all x in Zn, which are co-prime to n. So in other words, we're just going to randomly sample from this set. I'm just giving that set a name. Okay, so like we said before, choose x in Zn star uniformly at random. Okay. And then the claim is that with probability at least 1/2, two things happen. Number one, the order r, so let me write this in blue because it's a special parameter, of x is even, right? So that's the first thing we wanted. And why did we want the order to be even? Well, we wanted to be able to take r over 2, right? And because remember that once I had x to the r is equivalent to 1 mod n, then I took the square root basically to find something that satisfies x squared is equivalent to 1, y squared is equivalent to 1 mod n. And so this thing here, which is now well defined since r is even, this thing is not a trivial solution to x squared is equivalent to 1 mod n, meaning that it's not equivalent to -1 mod n. Okay, so this is the other main thing we wanted. So remember that we wanted a non-trivial solution to x squared is equivalent to 1 mod n. Okay. Okay, so once we have this, right, once we can find such an x, basically, remember from the previous exercise that is a non-trivial solution, basically, then remember we found a solution to, we said we can find a solution to this thing, basically, and then this thing allowed us to compute, let me just go back and remind you of these things, right? Right, so here we said that, if I can find something, an x with an even order, basically, so that it's non-trivial, a non-trivial solution, sorry, such that when we divide this thing is not equivalent to plus or minus 1 mod n, then, this thing, this y here, would indeed be a solution to x squared is equivalent to 1 mod n. And once we had that, then remember that we said that, well, you could factor this thing out, this expression like this, and we argued that, therefore, n, the factors of n would have to split up, some of which would have to divide this guy, and some would have to divide this guy. And so by taking this GCD or this GCD, we can extract a prime factor of n. Okay, so that was the kind of the sequence of how we got here. Okay. Okay, so this is the claim, and this is why the claim allows us to prove, or allows us to basically factor, if we can prove that this random sampling works. And let me just be very clear, we also had said a trivial solution would also be when x to the r over 2 is equivalent to 1 mod n. So why, and that's exercise, part of exercise 20, so why have I not explicitly stated that we're going to exclude the case with high probability that x to the r over 2 is equivalent to 1 mod n? Okay, why? Well, this is just because, by definition, r is the order of x, right? So there's no way x to the r over 2 will be 1 mod n, because then you'd have a contradiction. R over 2 would be the order, not r, right? So in that sense, that is just redundant. You don't need to state it explicitly. Okay, so let's prove it. And so in the proof, I'm going to use a number of kind of facts, which are exercises in the notes. In the interest of time, I'm not going to go through all of the proofs of these things. I might sketch some of them, basically. Okay, but again, I encourage you to kind of work through this section on your own. Okay, so what we're going to do, so I'm not going to prove it in all generality because the notation can get a bit cumbersome. And in particular, our goal is to break RSA in some sense. So which again we'll cover at the end of this lecture, section 4 of the notes. And so the case relevant to RSA is when n is the product of distinct primes p and q. Okay, because RSA starts by picking two primes p and q and multiplies them to get n. Okay. Okay, and once you have it for two primes, that you can certainly generalize it to more than two primes with a bit more work, but let's not go there. Okay, so what do we know about n? Okay, at least in theory, right? Sorry, let me try and keep this theorem here for now. Okay, so we know the only thing we know about n, is, of course, are its prime factors p and q, at least as far as the proof is concerned, right? And so step one, basically in our proof, is what we're saying is that we're talking about picking a random x, mod n basically, such that x is coprime to n. Okay. So now, but I want to kind of rephrase this idea of random x in Zn star, or so coprime basically to n, in terms of, in terms of the so-called local factors, which is just a name I'm making up, by the way. Okay, so in other words, I want to kind of be able to understand what does it mean to, if I randomly sample x, which is coprime to n, what does that mean in terms of the factors p and q? What am I randomly sampling on that kind of more local level? Okay. Okay, so this is one exercise in which I'll briefly sketch. This is exercise 22. And the claim is that choosing x in Zn star uniformly at random is equivalent to choosing a pair of integers. Let me give it just a bit more space. A pair of integers in a set that depends on p and q, which I'm going to define now. So this is a set of all integers a comma b, such that a is some number between 0 and p minus 1, for p a prime, remember, and b is in zq. Okay, so this is the claim that instead of sampling x uniformly at random from Zn star, I can equivalently instead just pick some a between 0 and p minus 1, and some b between 0 and q minus 1, p and q being primes. Okay, and those are the factors of n, remember, right? N equals pq. So that's the claim, and this local view is going to help a lot. And so why is this true? Well, this is just due to proof sketch. Okay, the proof sketch is just basically by the Chinese remainder theorem, right? Which said that, I can always write x, pick your favorite x, right? When I take x and I do mod p and I do mod q, right? Obviously, first of all, that's going to give me something, right? So if I fix x and I fix p, then obviously there's some remainder here, whatever that is, right? So let's call that a and let's call it b mod q, right? So that's going in the forward direction. And the Chinese remainder theorem told us that the reverse direction was also true, right? If you instead now think of, so here, think of, here, we fix p and q, right? And now you input x, and kind of, this is your output, right? X will define some a and b uniquely, obviously, right? And now we can view this in the opposite direction too, right? You can make it so that now we fix as input. So now these are fixed, right? And now instead, if I fix a and b, the Chinese remainder theorem tells me that there's always some output x that gives me a and b when I do mod p and q. Okay, and so this is by the Chinese remainder theorem. Okay, and in fact, x is unique, right? At least between 0 and p times q. Okay, so in other words, we have a bijection between, all this set, basically, Zn star, and this set over here, SPQ. So sampling X uniformly at random from this set is completely equivalent to picking A, comma B from this set. Same thing, okay? Good. So what have we learned? We've learned that, therefore, we can equivalently sample A, comma B, uniformly at random, of course, from this set SPQ. Okay, and so now that we have this, so now we want to do two things. Okay, remember that, let's just go back to what we have to prove, right? So all I did right now is I just rephrased what it meant to pick a uniformly random X in terms of local factors. And I need two things, right? I need to bound, when I pick X uniformly at random, equivalently I pick those local factors A, B. What is the probability that the order R is even, number one? And number two, what is the probability that X to the R over 2, assuming R is even, so this is well defined, that this thing is not equivalent to -1 mod n, that it's a good solution, it's not a trivial solution. Okay, so what I want to know is what is the probability of R is being even? And number two, what is the probability that X to the R over 2 is not in, well, okay, technically I write -1 +1, but remember the +1 case is not possible because X to the R is the order by assumption. Okay, so we need to bound the probabilities of both of these happening, and the claim was that, jointly these things will not happen with probability at least a half, I think we said. Okay, so let's first prove one. What is the probability that R is even? Okay, step one. Okay, so what do we know? Let's use green. Let's recall the facts that we have at our disposal. Well, I'm telling you already that, we're assuming that X, any X I choose has some order, right? So there's some order R basically, so that this thing is 1 mod PQ, which remember is just equal to n. Okay. And the other things I know by this Chinese remainder trick that we talked about is that, X is equivalent to some A mod P, and X is equivalent to some B mod Q, right? So these are the three things I know. And here what I'm going to do is I'm going to define RA and RB respectively, so that these are the kind of the local orders of X, right? So X to the R is equivalent to 1 mod P times Q, but mod P, the order could be different, right? So X to the RA okay, so what's the order of A basically, or B? Mod Q. Okay, so let's define the local orders basically. And of course, because X is equivalent to A mod P, this is completely equivalent to X to the RA, right? And this is completely equivalent to X to the RB, right? Just simply because, we have these equivalences, right? Mod P and Q. So you might as well replace A with X. Mod P, not mod Q. Okay? So these are kind of the basic things we could right away get. And now exercise 23, which I'll let you prove on your own because it should be similar to the previous exercise that we did that had to do with dividing orders. So what you can prove is that both RA and RB, right, which are, these local orders over here, basically, these guys must divide the global order, R. Okay, so R was, this order right here. Okay, so the global order mod PQ. Okay. Okay, so what does this mean? These local orders, they divide R, right? And so the conclusion, assuming you believe this exercise, so if RA, or RB, doesn't really matter, is even, then R is even, right? Because if if RA divides R and RA is even, it contains a prime factor of 2, then certainly R also contains a prime factor of 2. And so therefore the question is, what is the probability that RA is even? Okay. And this turns out to be a little bit easier to prove because remember, RA is not defined relative to this composite number PQ. It's defined relative to a prime P. Okay, and that's a bit nicer to work with. And this is proven basically subsequent to this main theorem. There's a lemma, which I opted to leave later because I kind of want to show you the main lemma first and its proof and how things fit together before we kind of fill in some additional details. And we'll see if there's even time to do it realistically. But it's in the notes, both the statement and the proof. And lemma 26 basically says that a uniformly random x in 0 to the ... p minus 1 has even order with probability at least a half. Okay? So this is lemma 26. In the notes, it's stated after this main theorem and proven there as well. And so basically, when we just plug in this theorem, what we'll see, therefore, is that this probability is at least a half, right? So we're talking about what is the probability that RA is even? That means that RA is even with probability at least a half. Okay? And likewise, this is true for RB as well, right? So together, this implies that RA is odd and RB, so the probability, I should say, that RA is odd, maybe a little bit less messy, and RB is odd, is what? Well, it's going to be at most a quarter, right? Because each of them is odd with probability. The only way they could both be odd is if you fail this test on both ends, right? So a half times a half is a quarter. Okay, so equivalently, at least one of them is even with probability at least 3/4. Okay, so this implies that at least one of them is even with probability at least 3/4, and hence R, the global order, which is divided by both of these local orders, R is even, the probability of this happening is at least 3/4. Okay? So that's the first thing we wanted to check. If I pick x uniformly at random from Zn star, with probability at least 3/4, it's going to have an even order, and so it's going to be well defined for me to define this x to the r/2 now. And now I need to check what is the probability that this solution is trivial or not. Okay, so let's do that now. So 2, did I do this with a color? I did. Let's be consistent. So what is the probability that x to the r/2 is in the set plus minus 1 mod n? Okay. And of course, this is assuming r is even. So we've already conditioned on passing the first step, which we just proved. Okay. So let's first make an observation. Maybe okay, let's just write here so it's a bit cleaner. So the observation is that since we know that x to the r is 1 mod p times q, or n, right? With a bit of thought, you can see that it's also true that x to the r is equivalent to 1 mod each of the primes individually. So and x to the r is equivalent to 1 mod q, right? And intuitively the reason is because, what is p times q? Well, it's just mod p, but q times, right? So if you think of it that way, you can convince yourself pretty quickly, hopefully, that indeed, both of these statements hold. Okay? Now, of course, r is not necessarily the order of x. It was the order of x mod pq, but it might not be the order of x mod p, right? There might be now a smaller choice of exponent that still mod p gives you 1, right? But certainly this at least holds. Okay, and so now we need an exercise. This is exercise 24. which states the following. It says for all primes p, the equation x squared is equivalent to 1 mod p. Okay, so again, it's very important that the modulus is prime, has precisely two solutions. Okay, what are those two solutions? They are basically x is either 1, they're the ones you might expect. X is plus and minus 1, right? So remember earlier we're looking for solutions to x squared is equivalent to 1 mod n that are non-trivial, right? That are not 1 and minus 1. And so that is possible because the modulus was not prime, but now the modulus is prime, right? So it turns out that modulus, when the modulus is prime, you really are kind of screwed. There are only the trivial solutions. Okay. Okay, so of course, why are we doing this? Well, intuitively, I mean, this is what we have here. Okay, we're going to get to that in a second. How do you prove this? Well, just think about, consider, just rewrite the equation again as x plus 1, x minus 1 is equivalent to 0 mod p, right? And now p is a prime, right? So think about all the numbers between 0 and p which p divides. Well, there are only two numbers, right? Either 0 or p. That's what it means to be prime, right? It doesn't divide 1, 2, 3 up to p minus 1. And so if this, what this is saying is that p is supposed to divide, this product. And so because p is prime, you can't break it up. So, p has to divide either this one or this one. That's the only thing that can work. And so in order for it to divide this one, this thing has to equal to either 0 or p, right? There's nothing else, which are of course equivalent mod p. And so how do you get that? Well, if x, for example, is p minus 1, or minus 1 equivalently mod p, then when you add 1, you'll get 0 mod, and then of course 0 is divisible by p. Okay, and likewise here, if I divide x to be, say 1, which is the other solution, 1 minus 1 is 0, and of course p divides 0. Okay? So, the upshot is that if my modulus is prime, then there are really only the solutions you would expect to this equation, which is x is either 1 or minus 1. Okay, so, why in the world do we want this? Well, we want to kind of characterize all the possible square roots, basically, because remember, what we wanted to do is, I'm looking at x to the r, mod x to the r is equivalent to 1 mod pq, right? This was my starting point. Because r is even, now I want to do a division by 2. I want to take the square root, right? That was our plan of action. And what we want to do now is characterize kind of all the numbers that can come up when we take that square root. Okay, and it turns out that, there are really only a very small number of possibilities. There are only 4. And we can kind of come up with all of them, characterize all of them by just looking at these local orders, because locally, when these are prime, the square roots of 1, when I take r over 2 here, and hence the square root of the right side as well, the square roots are very limited. They're only the trivial ones. Okay, so let's just put all that together. What does this tell us? Right? If I take the square root mod p of x to the r, and hence also of 1, and same thing for q, what we say is that x to the r has precisely, no more, no less, 2 square roots. Okay, by which, remember, I mean x to the r over 2, right? That's the square root. Mod p or mod q, right? And those square roots are 1 and minus 1, right? Those are the only 2 square roots we can get out. And so that means that one of kind of 4 scenarios has to hold, right? So I'm going to write down 4 scenarios. These are the scenarios. I'm just going to give them names, but it doesn't really matter. We'll call them A, B, C, and D. Let me draw A bit further back. And so each of these scenarios, basically, first I'm just going to write the same thing over and over again. If I'm smart, I'll be able to copy and paste it without rewriting it. Let's see if that's going to work. Let's take this full thing. Okay, let's see. Copy, paste. Hey, that worked, sort of. Let's see, did that work? All right, you know what? Did not. Oh, no, okay, let's not do that. I'm not entirely sure how to do that right. Okay, well, let's just rewrite it. Probably be faster. by the time I figure it out. So the only question, of course, is, just so you're thinking, maybe you'll already figure out what the answer is. The question is, what do I put in these gaps, right? What are the 4 possible ways to fill out these gaps, given what I've just told you about the possible square roots in mod P or mod Q? Okay. Good. So now you've had some time to think about it. So, for each of these, there are only 2 possible choices. It's +1 or -1. So there'll be 4 possible combinations, right? So, either this is 1, sorry, let's just do 1 and 1 first. Or you could have 1 -1, or you could have -1, 1, or finally you could have both being -1. Okay, and remember that, of course, -1 is equivalent to, say, P minus 1 mod P. Okay. Okay, so these are, one of these 4 has to hold. So for whichever choice of x I have in mind, right, when I take mod P, mod Q, with the square root of x to the r, right, one of these 4 kind of patterns has to come out, okay? And that depends on the choice of x. But remember now that, P and Q are co-prime, so specifying, these 2 right-hand sides of this equation, right, completely specifies what goes on the left-hand side, right? That's just the Chinese remainder theorem. You can go forwards and backwards between the global view in terms of P times Q and the local view in terms of mod P or mod Q, okay? So by the Chinese remainder theorem, each scenario yields a unique kind of global solution, x to the r over 2, which remember is equivalent to, it's just x to the r, of course, to the power half, because we took a square root. And, mod n, what was x to the r? Well, x to the r mod n is just 1 by, that was our assumption. And so really, this is just, 1 to the power a half, right? This is the square root of 1, basically, right? Okay. So in other words, what we're saying is that, each one of these 4 patterns, if you kind of interpolate, if you will, if you go backwards and you use the Chinese remainder theorem to come up with a global solution mod n, right, each of those will give rise to one of the square roots, basically, of 1 mod n. So in other words, there are precisely 4 square roots of 1. There exists precisely 4 square roots of 1 mod n, right? And x to the r over 2 is one of these, right? Okay, that's what this is saying. Okay, and so what are the 4 square roots? Well, so 2 such square roots are kind of the trivial ones, right? You always have the square roots 1 and -1. Those are always square roots of 1. So 2 such square roots are, where is this? 1 and -1. And these are, the bad ones, right? These are the ones we don't want. And now this is again going to be impossible. And remember, the reason why is because if it's true that x to the r over 2 is equivalent to 1, right? If it's that square root, mod n, then that contradicts the fact that r is the order of x, mod n, right? So x to the r was supposed to be the smallest exponent that takes you to 1 mod n. And so we know that it cannot be true that, x to the r over 2 is equivalent to 1. Okay, so this still kind of hangs around, though. This is the other bad case, which is essentially what the statement of the theorem was saying, right? We wanted to say this thing, right? Well, in the statement of the theorem, we only listed the second case, right? Which was, that's a pretty long theorem, huh? X to the r over 2 is not equivalent to 1 mod n, right? So this is the one we have to worry about, therefore. And so what are the odds that this is going to happen? Okay, so the conclusion is therefore let R denote the remaining 3 square roots of 1 mod n. Okay, i.e. those which are not equivalent to 1, right? Because we were able to remove 1, so there are only 3 left. Okay, then exercise 25 basically says that choosing x in z and star uniformly at random implies essentially, assuming that the order r was even, implies that x to the r over 2, the square root of n we get is uniformly at random from the set R I just defined. Okay, so again, R is just, there are 3 square roots. We're basically picking one at random. One of them is bad. The other 2 are good because those are the non-trivial ones. They're not 1 or minus 1. Okay, so this basically tells us that with probability at least 2/3, we get a non-trivial root of 1. Okay, well, maybe I should let me be a little bit more succinct. Okay, it's lagging again, so maybe after this section I can pause and reset. We'll finish order finding stuff, and then I could reset the journal. Okay, x to the r over 2 is not equivalent to minus 1 mod n. Okay, and so there are 2 things. So the probability overall of success, right, when I picked a random x was, remember, I needed the order to be even, and that was probability half. Sorry, that was not probably half, that was probably 3/4. Hello. Okay, and then once my order was even, then the probability that I got a non-trivial square root of 1 was 2/3, right? And of course, then we combine these and we get the value of half we were looking for the proof. Okay, so that is basically the proof, that we can reduce factoring to order finding. Okay, so just to recap, basically, remember we said that if I can find a solution to x squared is equivalent to 1 mod n, such that the solution is non-trivial, then I can factor n. Okay, I can rip out one of the prime factors. And then we said, well, how do you find a solution to that? Well, basically, it was sufficient to randomly sample x from Zn star in such a way that, number one, the order r was even, so that then I could take a square root. And the reason, remember, we took the square root is because we want to satisfy something squared is equivalent to 1 mod n. And so if I take the square root, then when I square this back again, I'll get x to the r, which is equivalent to 1 mod n. Okay, and the problem is that, I know something about x to the r, but I also need to guarantee that when I take the square root, I don't get a trivial solution, basically. So it shouldn't be minus 1. Okay, and the probability of that happening is at least a half. Okay, so you could repeat this, of course, this random sampling of x a number of times to bring the probability of failure, as low as you want. And then at that point, you could rest assured that with high probability, order finding will allow you to solve factoring. Okay, so let's see how long this has gone. It's an hour and a half. So what I'm going to do is I'm not going to prove. So there's a lemma in here, lemma 26, that we used during the proof of this main theorem. That lemma is stated and proven in the course notes. It's just a couple of lines, but in the interest of time, I'm not going to prove that in the lecture. You're always welcome to go to the lecture notes and look that up. Okay. But instead, in the remaining time, we have maybe about an hour left. I want to make sure we talk about the remaining part of the lecture, which is how do we use quantum phase estimation and continued fractions. And finally, just quickly go over how we break RSA. Okay, guys, so now that we've reduced factoring to order finding, now we can go ahead and solve the order finding problem using a quantum algorithm. Okay, so the algorithm will consist of two components. A quantum component, which is just basically quantum phase estimation, and a classical post-processing component, which is going to be this so-called continued fractions algorithm. So I'm going to start by telling you about how to do the first, the only genuinely quantum part of this whole algorithm, which is sampling via quantum phase estimation. Okay, so recall, therefore, the goal here is, given xn positive integers, such that x is coprime to n, what is the order R of x mod n, right? Oops. Okay, so basically what the quantum algorithm is just going to be an application of quantum phase estimation, but of course there will be a few challenges to this, right? It's not just going to be that straightforward. Let me just remind you very briefly, in phase estimation, the circuit looked like this. So this is figure 1 in the notes, but let me just do a brief sketch on the side to jog your memory. So remember, in phase estimation, what it did is you gave me an eigenvector of a unitary, and phase estimation gives us the phase of the corresponding eigenvalue for that eigenvector, right? So you plug in two things. Remember that this is going to be the eigenvector of the unitary in mind. This is going to be where the phase will get stored. So it starts with just being 0 to the n. And then we plug it into the circuit. And from last class we saw what we first do is, n Hadamard transforms in parallel, followed by a controlled u to the power k operation, right? So u, psi is an eigenvector of the unitary u, remember, and so the control here dictates, to what power we're raising u, basically. And then we did an inverse quantum Fourier transform. So if the details of that escape your mind now, don't worry. I mean, we're just going to use phase estimation as a black box now. This is just for you to, recall a little bit what this thing looked like. Okay, so now there are three questions we need to ask, right? Whenever you're going to use phase estimation, right? Number one is, of course, I'm trying to solve the order finding problem, and phase estimation requires me to plug in some unitary u, right? That's this gate over here, right? This one over here. So what is u, right? How do I encode order finding into a unitary? Number one. Number two in my list is, for phase estimation, I also need an eigenvector, right? So where's this going to come from? Okay. And last but not three, phase estimation, remember, had this funny thing where the amount of precision I get kind of coming out of the phase in this first wire, right? That will depend strongly on, the power to which I need to raise u here, right? So in particular, if you want n bits of precision, we needed to be able to raise u to the power 2 to the power n efficiently, right? So can we even do that for the choice of u, which we have not yet specified? So let's start with, the first challenge here. And once, we answer these questions, then we just plug in phase estimation as a black box. So challenge one is, what is u? Okay, so to what do we apply the phase estimation algorithm? And so the input to order finding is this up here, right? It's x comma n. So what we're going to do is we're define the unitary u. So of course it depends on this input x, because that's kind of like fixed as part of the input now. So we define a unitary ux. And again, I just need to specify its action on a basis. So I'm just going to specify it on the standard basis. So if I apply ux to some standard base element y, all it's going to do is x times y mod n, right? It's going to send it to the string which represents the answer of that computation. Okay, and so you can, the next two exercises, 27 and 28 in the notes, those exercises get you to convince yourself that indeed u is unitary, right? So that's the unitary u. Okay, and now let's try and understand, why does this work, right? Because ultimately, the point of this is that there's got to be some eigenvector I can plug in so that when I do phase estimation, the phase of that eigenvector is going to encode the order of x mod n, right? So let's think a little bit about what are the eigenvectors of ux and what do their eigenvalues tell us? Okay, so what we're going to do is I'm going to try and build some intuition by building the eigenvectors of u kind of from the ground up. Okay, so the question is, what are the eigenvectors of ux? Okay, so here's attempt 1. Obviously, I'm using the word attempt because it's not going to exactly work. But, I mean, let's think about why we defined u this way in some sense, right? So what do we know? Here are 2 facts we know, right? So number 1, I know that x to r is equivalent to 1 mod n, right? Just because by definition, whatever r is the order, it takes x back to 1, okay? And the other thing I know is that this operation, this one over here, right? The way, basically the defining operation of u, what does it do? It allows us to produce this infinite sequence, right? So ux produces sequence 1, then x squared, x to the r minus 1, and then of course it goes to x to the r, but that's just equal to 1 again, mod n, right? And then the sequence repeats itself, right? So if I start with 1 and I keep applying ux, it's just going to cycle through this sequence forever, okay? Good. So since we have this kind of cyclic behavior, right? If I keep applying u, I get the cyclic behavior. A natural way to kind of define the first, an eigenvector of u is the following, right? We might say, so let's just take a sum. First, let's just take all these powers. I'm basically going to encode the sequence, okay, into the kets. So I'm going to say x to the power j mod n. Okay, so this thing is going to cycle. There are only r values for this thing, right? So intuitively, we only expect r terms to turn up in the sum. And indeed, we're going to put j equals to 0 up to r minus 1 and 1 over square root r. Okay, let me give this a name. Let me just call it, for our discussion, eta. Okay, so that is a natural first attempt at an eigenvector. Why do I say it's a natural first attempt? Well, because what happens, right, if I hit this thing with u on the left, what's going to happen is that, each of these kets, like x to the j mod n, is going to get kind of upgraded to the next term in the sequence, right? So it's going to go to x to the j plus 1 mod n, right? And the very last term in the sequence, of course, this x to the r minus 1, that one wraps around and just goes right back to the beginning. So in other words, every time I hit this thing with u, right, all the terms will kind of take a step forward and the last guy will go back to the first slot, right? So it's just going to cycle through the elements basically every time I apply u. So if you think about this a little bit, you'll see that u times eta is just eta. Okay, so it's an eigenvector. Okay, so it's good in the sense that we know how to construct some eigenvectors now, at least one eigenvector. It's bad in the sense that, so now I have a u, I have something I can plug in as an eigenvector into phase estimation, but ultimately, what phase estimation does is it gives me the corresponding phase of that eigenvector, and that was supposed to encode the order of x, right? And clearly, the constant 1 is independent of x, so it cannot encode the order of x, okay? So that's attempt 1, and so even though 1 might not seem very exciting as an eigenvalue, it turns out we're actually very close to the right way to construct this eigenvector. So let's go to attempt 2. So what we're going to do is, we've used this wraparound property, right? That because the order of x is r, if we keep increasing the power of x, eventually it wraps around, then, this thing kind of goes over and over again. There's one extra degree of freedom I have not harnessed here, right? And that is, the phase. I haven't written a phase in here, right? So again, we have the cyclic property for the kets. And, luckily for us, when you talk about complex phases, there's also a cyclic property, right? The cyclic property is if you look at the roots of unity, right? I mean, if you go around the circle, eventually you wrap around and you keep going, right? And so the natural thing to do if you want to embed a cyclic choice of phases here is you're just going to put down the rth roots of unity, basically. Okay? So recall, if we define the principal rth root of unity, right, from last lecture, so it's just this thing, e to the 2 pi I over r, right? Then this thing wraps around, right? If you raise it to a sufficiently high power, namely r, right, then it just goes back to 1, right? You've gone all the way around the unit circle. And so now let's just do the same thing. Let's just plug these guys, right, into here, basically. Okay, so that when we go from j equals to j plus 1, not only will the ket kind of get upgraded to the next member of the sequence, but now, you know, omega r will get upgraded to the next power in its sequence. Okay, so then, and eventually everything will wrap around. So let's be formal, let's define this. So let's instead define 1 over root r, right, sum over j equals to r minus 1, x to the j mod n. Okay, so that was just eta from before, but now what I'm going to do is I'm going to put in e to the 2 pi I j over r, right? And so this is just omega to the j, right? That's all it is. Sorry, omega r to the j, right? Rth root of unity, rth principal root of unity. And let me give this a new name, right? So this is now phi. Okay. And now, well, first of all, this is interesting because now, of course, this thing actually has something to do with r in terms of a phase. And phases are, you know, we're a little bit closer to getting something out of a phase in terms of phase estimation. But of course, what we need to do is we need to check that phi is, as written, is an eigenvector of u, ux, and that the corresponding phase of that eigenvector indeed contains, you know, this little r, the order. So this is exercise, I'm not going to do it, but it should be fairly straightforward. Exercise 30, which states that ux times phi, it's none other than indeed phi, right? But it's going to be e to the 2 pi I and then over r. Okay? Yay, right? So there you go. So there's u. And so if I can only get my hands on this eigenvector phi, then, you know, I could run phase estimation in theory. And so therefore, quantum phase estimation on phi yields, remember it's going to be an estimate depending on how much precision I want, an estimate for 1 over r, basically, right? It's going to, the phase is 1 over r, the way we had defined it, I believe. Okay, so that's great, right? In principle, it sounds like you know, life is going to be good. Okay, now there's only one problem, which is, you know, how in the world do I prepare phi or phi, right? This thing over here. How do I prepare this vector, right? Because sure, if I knew r, then I could prepare this superposition with these phases, but I don't know r, right? I'm looking for r. So what do you mean? Hey, there's a chicken and the egg problem here, right? And so indeed, it turns out that it's not clear. So even though we've solved this problem of, you know, what unitary do we apply it on, and that it has like a good eigenvector, if you will, it's not clear how to prepare that good eigenvector. And that's challenge 2. Right, which is how to prepare phi. Okay. Now, the short answer is we don't. Okay. Okay, more accurately, you know, we don't know how to. And so we have to find a way around this, right? Okay. And intuitively, I mean, so let me first sketch the idea. The point is that, very roughly, what we'll instead do is we'll prepare another state, which is easy to prepare, and which has a quote-unquote nice overlap with phi, right? So that when you run phase estimation on this other state, which is easy to prepare, you know, some kind of fraction of it is going to actually simulate running phase estimation on the real state we desire, phi. So let me be a little bit more formal. So the answer is we don't, at least not directly. Okay, we don't know how to do that. And maybe you can even prove that it's equivalent to solving for r. You know, I haven't really thought about it, but it might be a nice exercise. Okay, so what we do is, you know, let's just extend phi to an orthonormal basis let's just call it B. Okay, so it's just going to be some set of states, and this is for the space Ux acts on. Right, so Ux is unitary, so whatever Hilbert space it's acting on, whatever number of qubits, let's just take phi as an eigenvector in that space, so we'll let that be the first phi1. I'll just define as what we were originally calling phi. Okay, so that's this guy. So I'll let that be the first element of the basis, and everybody else I'll just extend it to a basis for the full space. Okay, and of course, sorry, for the space, and let me give a name for the space, let's just call the space H. So any vector psi in that space, of course, can be decomposed in terms of this basis, right? So written psi equals sum over k, alpha k, for some coefficients that sum in square to 1 of phi k. Okay. Sum over k of alpha k squared is 1. Okay, and now, therefore, since phase estimation is just a unitary operator, in particular, this means it's linear. This means that if I plug into phase estimation, right? In phase estimation, I'm going to plug in, there were two registers, right? They were 0 to the n and my eigenvector, or it doesn't have to be an eigenvector, right? Is the point of what I'm showing you. Okay, so I plug these two things into phase estimation. This can just be rewritten as we just did in terms of this basis we defined. So sum over k, alpha k, I'll stick that there. And then here I have your phi k, right? So that was just this. And now if I apply quantum phase estimation, what it's going to do is it's just going to do things, it acts linearly, right? It's just a linear operator. So it acts independently on each of, sorry, that should be a phase, on each of the terms in the superposition. Okay, so this thing is theta k is an approximation to phase for phi k. Okay, so whatever eigenvector you happen to have in the superposition, the phase of that will get put next to it. Okay, and so kind of intuitively, if you were to just measure the first phase register now, then with probability absolute value of alpha squared, you'd see the phase corresponding to phi1, the one we actually wanted, right? Okay, and now so the question is, what should psi be, right? Can I come up with a psi, or in particular, can I pick a good choice of basis, right? So that I think we just, if we just take an equal superposition over these basis elements. So if I choose this basis here cleverly, and I take an equal superposition over the first r terms of that basis, where the first term is, of course, the real phi we want, can I make it so that, the psi you get, the full sum of all of them, is something nice that's easy to prepare? And the idea is as follows, right? I'm going to present it slightly backwards to the way it's written in the notes. So let's just think for a second. I have some state phi1, which I know exactly what it is, assuming I know r. I mean, if I knew r, then phi1 was just this state, right? And now what I want to do is I want to construct r minus 1 vectors orthogonal to this one, right? I want to fill out that basis. So how am I going to do this, right? So here I want you to think back again to the Fourier Transform lecture. And in particular, I want you to notice that essentially, up to relabeling of these basis vectors, now they're labeled x to the j mod n, but instead I could have just relabeled them j. This is nothing other than one of the columns of a van der Waals matrix, right? It's basically, you take the principal root of unity, and then you basically raise it to higher and higher powers, right? This is exactly what we did in van der Waals matrices. And remember that, the way we came up with the Fourier transform was we took that principal root of unity, and then we raised it to higher and higher powers to start each column. Okay, and then with each column, you raise each of the roots of unity to higher and higher powers. And in doing so, we came up with a set of columns, which were all orthonormal. They were unit vectors, orthogonal, and they gave us the Fourier transform. So we're just going to steal a page from that playbook. We're going to think of this as representing one column of a Vandermonde matrix. And so then we know exactly what the other columns would look like just by following the pattern of a Vandermonde matrix. Okay, so let me be a bit more formal now. Okay, so observe that phi1, which remember was just equal to phi, is just, I mean, it's approximately this up to relabeling of the Ketz. It's basically going to be a column of a Vandermonde matrix, right? Or a row if you like. So it basically looks like this. It's like 1 omega r squared omega r cubed dot 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 omega r to the r minus 1, right? If you look at phi, these are the phases you see showing up, right? And we already know how to come up with vectors orthogonal to this, right? The next column in the Vandermonde matrix looked like this. You would start with the square of that principal root, and then you'd square the square, right? Squared, square cubed, so forth, right? R minus 1. And so if we take phi and replace the phases in it, these guys with these ones, then you'd get an orthonormal vector. That's what Vandermonde matrices taught us. Okay, and so we're going to do the exact same trick now. I'm going to define phi k more generally in my basis for k going from 1 up to r, I guess, or 0 up to r minus 1, is going to be essentially the same thing as what we had before. So the black things I'll write, the black ink will denote what we had before, right? And the new part I'll write in red. So this we had before, we had over r, right? So this was the principal root because it's 1 over r, which we raised to higher powers j. And again, we had x to the j mod n, right? So that was just phi 1 right now. And what I'm going to do is I'm just going to add this k here. Okay? So you can think of this as none other than omega r k, right, all to the power j. Okay? So you're in column number k, and you're in row j, the way I wrote it here. Okay? So it's just like a Vandermonde matrix. Those things are beautiful, right? So this is really why I wanted to take the time to talk about them last lecture. Good. So this means that we get we can construct R, whatever R is, right, orthonormal basis vector, starting with the vector we want, phi1. And now something magical happens. So by the way, I'm not going to prove that these things are orthonormal. I mean, you get it more or less for free if you believe the Vandermonde stuff we did last class. But consequences. Number 1. Now, if I apply u to the kth such basis vector I created, right? What phase do I get? Okay, so it is going to be an eigenvector. And what you're going to get is e to the 2 pi I. So again, you'll have over r just like before, but what's new now is you have this funny k here, right? This is the same k. Depending on which of these basis vectors you chose, you're going to have k in your numerator now. Okay, and I'll come back to this in a second. Kind of the more interesting thing now, before we get, I mean, that's interesting too, but slightly more relevant at this moment, is that magically, if I take phi k and I just sum them all up with equal weights, r minus 1, and I have to, of course, normalize them because they're all orthonormal. What state is the sum? It is nothing other than essentially the binary encoding of the number 1 mod n. Okay? This is trivial to prepare, right? I mean, the state encoding 1 is easy, right? So magically, I don't know how to prepare phi 1, phi 2, or any of them, right? But if I can prepare 1, which is trivial, you could always think of that as just being a superposition of all those states uniformly. Okay? So magic, right? Black magic, right? Good. Okay, so now if I combine these two, if I take both of these guys together, what does it tell me, right? Well, it tells me if I prepare, when I run phase estimation, right? What am I going to do? Let's go back to the picture for phase estimation for a second. If over here, you know, I plug in 1 mod n, right? And then I run phase estimation. This thing is a superposition of those R basis vectors I constructed. And then I measure, right? So I prepare one mod n, and I run quantum phase estimation, right? And so this was my state psi that I was trying to construct. That was this nice state. And what's going to happen is that, so measuring the first register in the QPE diagram yields, so now I have a superposition, right? This state is not one state, it's k states, right? And they're all equally weighted. So with probability 1 over r, it's going to be uniform. So with probability 1 over r, we're going to get the phase corresponding to the kth, whatever, for each of the k's, to the kth eigenvector phi k. So you're going to get the phase corresponding to the kth eigenvector, which would be k over, and again, I'll do this in black just so you know it's the old version. Okay, so the k is the part that's new. So measuring the first register uniformly at random gives me k over r for some, for clarity, k in 0 up to r minus 1. Okay, so this means that what we can do efficiently, given the quantum phase estimation algorithm, is we can do this. Well, I still can't figure out r necessarily, right? If you gave me 1 over r, then of course I could invert it to get r, right? But you're not giving me r, right? You're giving me k over r for some random k, and I have no idea what k is, and of course I don't know what r is, right? So if you just give me k over r, you know, a priori it's not clear how to extract r, okay? So, so what have we learned? We've learned that we can sample uniformly at random from the set, I gave it a name, S equals to 1 over r, 2 over r, up to r minus 1. I guess this will be a 1 here. R minus 1 over r. Okay? So every time I run phase estimation, I measure, basically, I get one of these phases uniformly at random. Okay, and obviously if I get 1 over r, I'm happy, I just invert it. But, you know, r could be very big, right? R in principle can be as large as the order n. Sorry, as the original prime composite number we're trying to factor n, so which is exponentially big in the input size, right? So, you know, the set is very, very large. It might take me a very, very long time until I sample to see this 1 over r. Okay, but nevertheless, I can do this sort of sampling, and the question is, you know, given a random sample from the set, can we recover r? Okay, so that's the question. Given a random sample from S, can we recover r? Okay, and the answer is yes. Again, more magic, by something called the continued fractions algorithm. So we're going to get to that in a second. Okay, but before that, there's one more thing we have to deal with, which is the third challenge in using phase estimation, right? And the question is now a matter of precision. So how many bits of precision do we need, right? So, you know, my phase estimation algorithm will give me an estimate of, you know, k over r, randomly sampled, right? Right up here. But of course, it's not going to be perfect, right? K over r might not even have a finite expansion, right? So, you know, I'm only able to approximate this to within some number of bits of precision. So the question is, how many bits of precision do I need to recover r, number one? And number two, whatever that number of bits is, let's say that number of bits is n, I then need to be able to implement u to the power 2 to the power n. Okay, so I need to be able to do that efficiently. Okay. Okay, so, you know, question, can we efficiently run QPE to the precision required to recover R from, and this is now going to be an approximate sample K over R. Okay. Okay, and so to answer this question, right, so let's just recall that the input to factor was this, the composite number n. Technically, we also had a threshold, but let's just forget about that for a second. So input to factor, which is just the integer n. Its input size is encoded via, and now I'll define little n to be the number of qubits, or bits, sorry. Let's be very precise. Log base 2, ceiling plus 1. Okay. So that's the number of bits you need to encode it. So basically log n is the point. Okay, so everything I talk about will be in terms of little n because this is your input parameter, right? This is the size. You need to run in time polynomial in little n to be efficient. Okay. And now just a cute exercise, right? So suppose, just to get a sense of what we're up against, right? Suppose I have two positive integers, k and r. Let's just say k is smaller than r. And these are both representable exactly in just n bits. Okay? And so the question is, how many bits to express now the ratio? Okay? And by bits, I mean, I want a decimal expansion like B1, B2, right? I don't mean some other succinct encoding, right? And so, okay, because we know that basically, for example, little r, requires only little n bits because it's at most capital N in size. So I have a bound on how big k and r are going to be. So can I bound how big k over r will be? And the answer is not necessarily, right? Let's do a very quick counterexample. So if you want, you can take a moment to pause the video and think about a counterexample to this claim that, in fact, in general, this expansion might be infinite, even though k and r could be represented using a finite number of bits. So here's an example, counterexample, that suggests there is no bound in general, which is, if k equals to 1 and r equals to 3, right? Both of those can be represented using 2 bits, but the ratio is 1/3, which has an infinite expansion, right? So just as a very simple counterexample. So the point of this is that even though I know bounds on the length of k and r, I don't necessarily know bounds on k over r. Okay, so let's try and get a bit of the exact number of bits of precision we'll need for k over r will turn out, to come from a theorem later when we talk about continued fractions, but we can maybe get a little bit of intuition just by being blatantly stupid and making wild conjectures. Okay? Okay. So the answer is that no a priori bound, right? In general, it could be unbounded. Okay, but let's try and get a bit of intuition, right? If k and r are n bits each, right? Then, I mean, if you stare at this long enough, you'll realize that, k times r as a number, as another integer, requires something like 2n plus 1 bits to write down, right? Basically, the number of bits is going to double, okay? So you might somehow expect, waving hands again here, I'm not saying this is rigorous, that therefore, in big red, maybe, question mark, right? K over r can be, the character of it, if you will, in some sense, or that's not a formal term in this setting. Maybe k over r can be sufficiently approximated, at least for the purposes of recovering r, with 2n plus 1 bits. Okay, so since the product requires that much, so maybe we can take this same number of bits as an estimate for k over r instead. Okay, because k over r is also technically a product, right? It's a product of k and the reciprocal of r. Again, this is just trying to give you some intuition. And it will turn out that indeed 2n plus 1 bits will suffice. If we can estimate k over r to 2n plus 1 bits using quantum phase estimation, then continued fractions will work. Okay, we will be able to recover r. Okay. So again, we'll get to continued fractions in a second. So later, 2n plus 1 bits will suffice. Okay, good. Now, fine. So we want to, so therefore, we want to run quantum phase estimation to 2n plus 1 bits of precision. Right, so in that first register in phase estimation, where the phase comes out, the number of bits there, should be the number of qubits is 2n plus 1. Okay, and we want success. Remember, QPE is not perfect, so it had some success probably, which we are allowed to play with. So let's say we want probability of success at least 1 minus epsilon for some small epsilon greater than or equal to 0. Well, sorry, strictly greater than 0. Then, what did we have to do? We had to do two things, right? The first register of QPE, instead of setting it to be precisely 2n plus 1 bits, so I mean, let's just, rather than me frantically waving my hands, let me just show you this diagram again, right? So, the phase is going to pop out here. So instead of making this 2n plus 1 bits to store that many bits of precision, remember we have to grow it slightly larger so that to increase the probability of success. So how much bigger did we have to grow it? The analysis from last lecture said that we needed to set it to n prime being, that's the size of the register. This is what we wanted, 2n plus 1, plus a small overhead, basically. So something plus, the ceiling of 2 plus, so basically the log of 1 over epsilon is really what you're looking at here, right? So this is going to be the number of qubits in the first register of phase estimation. That alone is not a huge problem. We just grow the register a little bit, okay? Now, the more annoying part is that if I want to set n prime to that, then I need to raise, u to power 2 to the n prime, right? So I need to be able to run u to the 2 to the n prime, which is of course just in 2 to the n prime is of course order 2 to the n, right? This thing is huge, right? Okay, so that's exponential, of course, in our encoding size, right? And so how are we going to do this? So let me be clear, what does this mean, right? What we really want to do equivalently, what we are saying is that we want to be able to compute, what did u do? It just, did x times y mod n, right? But if I raise u to a very high power, whatever that power is, it's just the same thing as, multiplying by xk times. That was just the definition of u. Okay, for k in order, 2 to the n basically is what it boils down to. Okay? And what we need to do is, of course, we need to do it in time poly n, right? That's the input size, not 2 to the n. Okay? So a priori, it seems like you're in a bit of trouble. You want to exponentiate x to this extremely large power, right? Efficiently. How in the world do you do it? So if I could draw a superhero, I would, but I'm really bad at drawing. So I'm just going to write down the name of the algorithm which will solve our problem, which is the so-called square and multiply algorithm. Okay, so there is an algorithm that will do exactly this, right? Which is that if I have an x, well, not exactly this, slightly off, basically it will allows us to compute x to the k mod whatever you want. Let's just say n. Well, let me give it another name just to be clear that it has nothing to do with n in this particular case. For, k can be as big as 2 to the n if you like. It doesn't matter. Okay, it's able to do it. So it can do this exponentiation efficiently. Okay, and it's a classical algorithm, so what we can do is we can do this basically coherently in quantum superposition, basically. Okay? So just a quick sanity check, right? I mean, if I'm taking x, whatever x is, even if it's a constant number of bits, and I raise it to 2 to the n, let's say, the size of x is going to blow up dramatically, right? There's no way I'm going to be able to express x to the power k explicitly. So how do I get around this? This is, no, it's not an exercise. Well, keep in mind you have this mod hanging around, right? And so that just means that whenever your number gets too big, let's say after each time you multiply through by x, you could always, apply another mod m and kind of squish things back down to this nice manageable space. So it's very important here for square multiply to even make sense as an algorithm outputting something I could even hope to write down, that we're working modulo m, or some number m, so that, the number x to the k, I can control how much it blows up, basically. Okay. Good. So I'm going to rewrite this slightly differently. Okay, so maybe I'll just write what's in the notes just to be consistent. So this computes basically, a to the power b, whatever a and b are, right? Mod m. And how many field operations does it need? It needs something like polylog of the exponent b. Okay. Maybe I shouldn't call them field operations. Maybe it's a ring operation because m doesn't have to be prime. But anyway, you get the point. Like, I'm not talking about bit complexity here, right? I'm counting the number of multiplications you have to do, for example. Okay. So, and so naively, what would be the cost of doing this? Well, you'd have to multiply a by itself b times. That's a super naive way. And so square multiply doesn't take, b multiplications. It takes polylog b. So it's exponentially faster. And that's, of course, what we need, because in our case, b is huge. B is an exponential. So, this log will get rid of that exponential for us. Okay. So what is the square and multiply algorithm, right? If I want to do this phase estimation, I want to raise u to a very high power, meaning equivalently, I want to, do this classical multiplication to high powers. How do I do it? So there's a basic idea, and then there's a simple way to generalize that to more general inputs. So let me just give you the basic idea that kind of has everything you need. And let's just suppose b is a power of 2, right? So here I'm expanding, b is just the exponent, right? So let's just suppose that exponent is a power of 2. So maybe I'll say that b equals 2 to n. Okay? So trivial observation, really trivial. Here's your observation. This is the magic of the entire scheme. Okay, if I want to talk about a to the b, right, that's completely equivalent. Okay, fine, we can do mod n, just to be precise. That is completely equivalent, whether or not you have the mod n, frankly, to first doing a squared. But then, of course, you get to the trade-off is that I get to cut the exponent down in half. Okay? So again, this looks completely trivial if you stare at it, but it does bias something, right? Basically what this is saying is that instead of if I raise a to the power b, that's completely equivalent. Instead, I can cut the exponent, the expensive part, right in half, as long as I don't start with a, but I start with a squared instead. Okay, trivial. And that's precisely what square multiply does. Okay, it just basically says that it will recursively apply this idea, right? It will recursively keep cutting the exponent in half, basically. And instead, it just squares, this underlying term that it's got here. Okay? So you just apply this recursively, right, until basically b goes to 0, or I guess to 1 technically, or whatever. Okay, but that's the basic idea. And how many times can you do this? Well, and each time I do this, by the way, of course, I'm doing a square operation, right? So I have one multiplication. Well, I'm dividing b by 2 each time. So, the number of iterations of this is going to be at most the log of b, right? That's the beauty of it. That's where the b comes from. The log b comes from, right? Good. So that's the basic idea when b was just a power of 2 in this exponent. And, basically we have to expand this now to other powers, which can include, other odd numbers in their prime factorization, right? So the general idea, and I won't really spend too much time talking about this, but or the general case. So this just means that b is not a power of 2. So if b is not a power of 2, then we update the recursive step, basically. So basically we have to apply one of these two cases, depending on whatever b is, right? There'll be two cases. So in the previous basic idea. You know, we're always in this case, right? B was always even because it was a power of 2. But if you have factors in there that are not even, then, you know, when we keep dividing b by 2, eventually you're going to hit an odd factor, right? And then you have to worry about b being odd. That's how this is going to show up now. And, you know, this is just exactly what we had before, right? There's nothing new here if b was even. So the new one is this one. What do we do? Well, again, I'm going to have an a squared, just like before. But because it's odd, I have to strip off one extra factor of a. So there's that guy. There's the extra factor that was contributing to that oddness, if you will. And then, of course, I stripped off a factor of a, so I have to subtract 1 from b, because now b used to be odd, and now it's even. And then, of course, now I could divide by 2, because b minus 1 is even. Okay? That's square and multiply. Okay, so now just keep applying this until b goes to 0, and you will have computed a to the b using just a log number of iterations. Log b number of iterations. Cool, right? This is a nice trick to know in general. I mean, it's not unique to, it's very well known. It's certainly not unique to the quantum factoring algorithm. Okay, and we'll see, for example, later on when we talk about RSA, I mean, you would use this thing even in RSA, because there you have to, in general, compute things to high powers modulo some n. Good, that's it. Okay, so what we've concluded now is that we've met our third challenge, which is that, well, we met all 3 challenges. For phase estimation, we've specified the unitary that we're going to run. We've specified how to get around the fact that we don't know how to prepare an eigenvector encoding the order of x. And number 3, and so as a result, we've been able to get samples of the form k over r, where r is what we're looking for. And we also have come up with a way to run the controlled unitary operation in phase estimation to a sufficiently high power, basically efficiently. Good. So now we're left to the last phase of the phase estimation, the factoring algorithm, which states the following. 3.3, post-processing via continued fractions. And here, you know, some things, well, actually, I don't think I'm going to prove anything, but, you know, I'll state theorems at least explicitly and explain how things fit together. And so let me just remind you. So in section 3.2, we use quantum phase estimation to uniformly at random sample. I guess I should have said sample uniformly at random from the set S equals to 1 over R, 2 over R, dot, 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 R minus 1 over R. Okay? And so in particular, what we really got was letting n equals to basically the log. So this was the encoding size, right, of the input. So each time we run phase estimation with probability at least 1 minus epsilon, we get a 2n plus 1 bit approximation to a uniformly at random choice of k over r. Okay, some element of s, right? So I guess I should do this. Okay, and now the question is, you know, extract r. Right? So again, I don't have k over r exactly, right? I have some finite approximation to k over r. That's this 2n plus 1 bit business. And from that, I want to, number 1, identify the exact fraction k over r. And then once I have that, I want to extract r itself. Okay, that sounds impossible. I agree with you, but it can be done. So before we show how to solve that, using the magic of continued fractions, let me just briefly mention a minor obstacle, right? Which is the following. If I look at k over r, right? R, the order, is not necessarily prime. It can be anything, right? It's just some number between 0 and I guess 1 and n minus 1, right? And so it's entirely possible that k over r is not in lowest terms, right? Maybe k and r share a common factor. And that's bad news because r is not uniquely determined then in some sense, right? If I want to have any hope of extracting r given k over r, I'd better hope that k and r are going to be coprime, so that, this is already in lowest terms. So as long as I could figure out the denominator of this thing in lowest terms, I'm done. I'll know what r is. Okay, so if k and r, so basically if we want to have any hope of extracting r, we need k and r to be coprime. Okay, otherwise that fraction k over r is not in lowest terms. Okay, and so there are various ways you can get around this. I'm going to give you just the simplest one because, again, it's just elegant and it just does the job. Okay, so it turns out that, since, k is basically in the range, it's basically an integer smaller than r, right? If we just pick, since k is being picked uniformly at random, if the number of numbers smaller than r coprimed is sufficiently large, then that means with high probability we're going to get exactly this property, that k and r will be coprime. And actually there's a quantity exactly for this. So if you go look up, Euler's totient function, okay, and in this case it would be phi of r. That function basically is just literally the number of integers, I guess natural numbers smaller than r, which are coprime to r, right? And there are estimates for this number, and roughly speaking, what you're looking at is this thing is larger than r over log r. Okay, it's something like this. Okay, so in other words, the vast majority of natural numbers smaller than r are going to be coprime to r. Okay. And since we're picking k uniformly at random from the range 0 to r minus 1, then that means with very high probability you're going to get indeed k and r being coprime. Okay, so you could repeat this repeat the whole experiment like this QPE a few times, and with high probability you'll see a sample k over r where k and r are going to be coprime. So that's all I wanted to say. Henceforth, we're just going to assume that k and r are indeed coprime, and that means that the ratio, henceforth assume the ratio k over r is in lowest terms. Okay, so if I could figure out the denominator of this ratio, then it will tell me exactly what r is. Okay, so now I can tell you about the continued fractions algorithm. So, continued fractions. So what is continued fractions? In a nutshell, basically, if I have a rational number a over b, right, let's just assume that a and b are going to be some positive integers, right? Continued fractions is just, or the continued fractions expansion, as it's called, is just an equivalent way of writing this rational number a over b. That's all it is. Okay? Okay, so it's going to be an equivalent expression for a over b. It's just another way of writing it down, right? But of course, this way will have its own advantages, right? So instead of writing a over b, instead what we're going to do is we're going to write a larger list of integers, c0, c1, that's a typo in the notes, okay, cm, right? And what is the relationship between a over b and this funny sequence c I've written down? Well, the fraction a over b equals precisely what happens if we do this. So first we take the first term, here's c0, right? And then what you do is you invert, and then you take the second term, c1, okay, that's this one, right, and so forth. And now you keep repeating this, add and invert, right? Plus 1 over c2. Okay, and as you can see, this is going to get a little bit messy, plus dot, 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 and eventually you're going to get something like plus 1 over cm. Okay, so that's the continued fractions expansion of a over b. Okay, it's just this weird, funny recursive structure where you just add the next term ci, and then you invert the rest. Okay. So why in the world would you do this, right? We used to have two numbers and now we have m numbers. So, we just made things more complicated, right? Well, there's of course a huge benefit for us, which is the following. So note that technically speaking, if I were to use all the coefficients in this expansion, right, then indeed I recover a over b. But I can instead think of this as a sequence, not just a single rational number, but really as representing a list of rational numbers or sequence of rational numbers, right? Because, in this kind of expansion process where I keep adding and inverting, I don't necessarily have to use all the way up to m, right? I could maybe just use C0, C1, C2, and then I'll just have 3 layers of this expansion, and that's some rational number. It's not a over b, but it's something I could still write down, right? And so, in particular, we define or give this thing a name. CK is just going to be the subsequence of C, which is just 0 up to the kth term. Okay, we don't go all the way to the end. We don't go all the way to m. This is the kth convergent. Okay, and this is just a definition. Okay, and so what did we have in phase estimation, right? What we had is that, we don't have k over r, right? What we have is a very good approximation to k over r. We have a rational number. Okay, so maybe I should remind you. So QPE gives a finite, meaning 2n plus 1 bit approximation to k over r. So in particular, so let's call this our approximation just x for now. So x is 2n plus 1 bits, and it approximates k over r. That means k, by the way, is rational, not because it approximates k over r, but because it has a finite binary expansion, right? So it's certainly rational. So this is rational, and that means that in principle, I could write down the continued fractions expansion of x. Okay. Also in practice, I could do it. And the other thing I know is that x reproduces k over r to quite high precision, right? It gets the first 2n plus 1 bits. So in fact, this funny rational number x is quite close to k over r. And the point is that if I take the continued fraction, so if x is a rational number that's very close to my target, it turns out that if I write down the continued fractions expansion of x, then there exists a convergence. So if I cut off the sequence at the appropriate point, the continued fractions expansion I would get for that convergent would give me exactly k over r. So in other words, even though x is just an approximation to k over r, it would give me a way to basically snap x back to k over r exactly, in some sense. Okay, to kind of round it off. So let me give you the theorem that states this. We're not going to prove it. It says we have k, r being positive integers. X is a rational number. That's what this q is. And these guys satisfy the following bound, right? So I want k over r. That's not what I have. Instead, I have the estimate x. That's what we have. Okay. And as long as the estimate is good enough, right, it's close enough. So what does good enough mean? Well, it's smaller than, whatever 2r squared is. Okay, so notice how r is, of course, the same. This is the order in our case, right? As long as this is true, your estimate is close enough, then if we say, again, C is going to be the continued fractions expansion of x, right? So so this is what we get out of phase estimation in our case. It's very close to what we want. So if I take the continued fractions expansion of x, call it this, that's taking it all the way to the end, then there exists an index k in this expansion such that that kth convergent, meaning if you just expand this thing up to order ck up to c0 up to ck, this thing represents k over r exactly. Okay, so that's amazing, right? So even though I have this weird approximation to k over r, there's a sense in which I can recover k over r exactly. Okay, and so exercise 39 asks you to double check that, since we use 2n plus 1 bits of precision to approximate k over r, you can check that indeed, this bound holds. Okay, so I'll leave that as an exercise. Okay, so, this almost gives us what we want, because this means that, given my funny approximation x, I can get k over r exactly. In particular, I get a continued fractions expansion of k over r. So, therefore, given x, can extract a continued fractions expansion of k over r. Right? That's what I've got so far. And of course, let me just make a quick comment. A priori, we don't know which convergent for x, right, is supposed to give us k over r. That's not obvious. I mean, if you look at the proof, obviously you can figure out which one it is. But if I just give you this expansion, it's not clear which one it should be. But you can prove that, and I think we're gonna get to that in a second. Yes, we're gonna do that in a second. It turns out that this m, the number of terms in the expansion, is always polynomial in the encoding size, right? So you can actually just try all the convergence and see if you're able to extract a proper order r and then factor your integer n. Okay, so you can just try all the convergence is the short story. Okay. Okay, so given x, we can extract the continued fractions expansion of k over r. Okay. Okay, but we don't want that. We want r, not k over r, right? So now I know exactly k over r, but of course now I need to still get r. Okay, so there are 3 questions left, right? Number 1 is how large is m in theorem 38? Okay, so if I look at, this m over here, right? I'm taking the continued fractions expansion of x. How big is it? Well, it turns out that, and we won't prove this here, it turns out that since k and r are n-bit ints, we can choose m being order n. Okay, so the point is that, the number of terms in the expansion does not blow up exponentially. It's fine. It's just linear in the input size. Okay, so that's very good. There's just a linear number of convergence we would need to cycle through to figure out which convergent gives us k over r. Okay. And now the other 2 things that I haven't really told you about is, well, number 1, if I started with x and I said I compute the continued fractions expansion of it, well, how do I do that? Right? I haven't told you that. And number 2 is once I've got my hands on the convergent of this thing, which really does give me k over r, then how do I extract r? So those are the last 2 things we have to quickly discuss. So number 1 is, let's show how you would compute the continued fractions expansion. Okay. And so the algorithm is very simple, actually. There's no magic to it. It's kind of like what you would come up with if you just stared at the expansion long enough and tried to reverse engineer it, like literally. So it's literally trying to implement, you start with a over b, and then you literally try to strip off a term and then invert the rest, and you repeat this over and over again. And the only question is, well, what do you strip off here? And the rule is going to be greedy. Okay, it's a greedy algorithm. It's going to strip off the largest integer it can, and then it's only going to have a rational component left, and it's the rational part it will invert, and it will repeat. So basically we want to, if I call this equation star, we want to implement this star basically in a greedy fashion. Okay, so let me give you, best way to do this is via an example. So the idea is to implement equation star greedily, quote unquote. And let's just start with this example, 23 over 9. Let's write down the continued fractions expansion for this. So remember what we did is that you always split off a term and then you invert the rest. That was the trick. So first, the split will make it greedy. We will split off the largest integer possible, right? So 9 goes into 23 2 times plus some remainder. So that's the integer part. And the fractional part is this one, 5 over 9, right? And now I'm going to invert. Now I do the inversion step where I invert the second half of this, right? So it's 2 plus 1 over, and then maybe I'll write this in red. This is 9 over 5. That's just the inverse of this thing here. And now I just recurse on the 9 over 5. Exactly the same thing over again. right? So again, I'm going to have a split step, which is just 2 plus 1 over, and now 9 over 5, well, that's just 1 plus 4 over 5. Right there, I just did my split step. And now I do my invert step again. So I get 2 plus 1 over 1 plus 1 over 5 over 4. Let me just do it this way. There we go. Okay. And I think we just need one more and we're done. So I'll just cram it here. So one more split step, which is, let me just move this slightly over to the left. Hello. Screen does not want to move. Oh, maybe it did. Did it? Anyway. 2 plus 1 over 1 plus 1 over 1 plus 1 quarter. Right? And now we're done because, you know, the last rational number I came up with is 1 over something, right? So now I'm done. So that is the continued fractions expansion for this number 23 over 9. Okay. You can prove, I won't do it, exercise 41, that if you start with any, well, I mean, we've sort of already given away the answer, right? We said that the continued fractions expansion will have, if each of these guys takes n bits to write down, then, you know, the expansion will need only order n steps. And that in particular means that, of course, this thing is finite, the expansion. So this tells us, you know, given the x that we got from our QPE estimate, quantum phase estimation, I can compute the continued fractions expansion of it. One of the convergents will be what I'm looking for, k over r. And now, given that convergent, whichever one that is, I want to invert it and extract back the numerator k and the denominator r. And that's the last thing we need to cover for the algorithm, the factoring algorithm, which is recovering r by basically inverting the continued fractions expansion. So I'll just write CF from now on. I probably should have started doing that much earlier. Okay. And, okay, so basically the idea here is that, so having computed now C equals to, you know, C0, C1, dot, 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 Cm of x. Remember, this is the x is not k over r, it's the estimate of it, right? So by, sorry, let me just remember which theorem this was. So by theorem 38, we can try all convergence of x till we hit k over r, the convergent for k over r, right? And this will take polynomial time because we said the number of convergence is polynomial in the encoding size of little n. And so given the convergent now for k over r, so therefore given the convergent for k over r, we apply this theorem. Okay, so what theorem is this? It's the final theorem, which is theorem 42. And it states the following. Given, you know, whatever the kth convergent is, convergent ck equals to c0 up to ck. These are all positive integers. And then what we'll do is we'll define, you know, again, you can cut off this convergent at any point, and that will give you another rational number. And so let's just define that sequence of rational numbers. Define basically ai over bi as, and we'll do it recursively. So the very first choice, a0, b0, that's just going to be c0 and 1. And the exact things I'm going to write down don't really matter. The point is what will come out of this theorem, right? But let me just show it to you for completeness. 1 plus c0, c1. And finally, ai for I in 2 up to k. This equals to ci, ai minus 1, so you see it's recursive, plus ai minus 2. Okay, and you could probably just reverse engineer this just by staring at that equation star, which gives you the continued fractions expansion. Okay. So in particular, then the expansion ck, so if you really take the full expansion, then it's equivalent, or any partial expansion, to ak over bk, right? So if you cut the expansion basically at any point, that will be equivalent to the fraction, whatever point you stopped at, let's say ai, it'll be ai over bi, whatever that fraction is. Okay. So basically, this gives us a way to, given a continued fractions expansion, to recover the ratio to which it corresponds, and ak and bk, if you stare at the proof long enough, you'll see that they're actually coprime. Okay, so ak over bk is in lowest terms. And that's exactly what we wanted, right? Because remember, we assumed that k over r was in lowest terms, right? K and r were coprime. And therefore, if I have the continued fractions expansion of k over r like this, or sorry, whichever conversion it was, this one, then I can apply this theorem. I could just invert the sequence C0 to CK to recover basically k over r. And in particular, I won't just get k over r, of course, I'll get both the numerator and the denominator separately. It'll break them apart for me. Okay? So by combining theorem 38 and 42, can recover k and r from k over r. Okay, that's the trick. Boom. Okay, that's the full factoring algorithm from beginning to end. Okay, so just to quickly recap, we started with reducing factoring to order finding. Then we used quantum phase estimation to sample elements of the form. So if the order was r, we sampled k over r, the numbers k over r, uniformly at random, for k between 0 and r minus 1. And finally, given those samples, we showed how to extract r using continued fractions. The only part of that algorithm which is quantum is just the phase estimation. Everything else is classical. Okay, and so that is the full factoring algorithm. Why do we care? Because it breaks RSA. So let's just take maybe 10 minutes and wrap up the lecture by showing how breaking factoring allows you to break RSA. Okay? I mean, you can't have a full story unless I think you see this. So that's the final section in the notes. And now we can apply this to break RSA. Okay, so I'm going to go over this briefly. I'm not going to prove anything. That's not the purpose of this lecture, of course. But basically, what is RSA? RSA is a crypto system, right? And you imagine that you have a party. So in the notes, I called her Alice, right? And what Alice wants to do is she wants to make it possible for everybody else in the world to share her secret messages, basically, so that she can read the messages, but nobody else other than her and that particular sender of that particular message can read that message. Okay? So how do you do that, right? Well, what she does is she prepares basically, she keeps the RSA, well, okay, what is RSA? It's called the public key crypto system. Okay, and what does it mean to be public key? Well, basically what this means is that the scheme will consist of two things, which we'll define. There will be a secret key S that Alice keeps in her possession, and this is what she uses to decrypt incoming messages. And what she will do is she will broadcast out a public key, K. I think I called it P in the notes, right? Okay. And so that's public knowledge. So anybody who wants to send Alice a message, they would use P to basically encrypt whatever message they have in mind. And they would send that off to Alice, and Alice would decrypt the message using her secret key. Okay? So it's one way in this regard. Security is kind of incoming to Alice. Okay, so let's just very briefly define how RSA works, and then we'll observe, quite obviously how being able to factor is going to allow us to break RSA very easily. So maybe I'll do A, B, C, D. So in RSA, how does Alice create the keys, the secret key S and the public key P? Okay, so she just follows these steps. It's going to obviously involve modular arithmetic, just like before. Okay, so what does she do? She chooses large distinct primes P and Q, and she computes n equals PQ. Okay, so this is why we were talking about factoring integers n, which are a power of just 2 primes. So she randomly chooses a small odd element e of the integers, which is coprime to this funny thing, so p minus 1 times q minus 1. Okay, and so she knows p and q, so she can also compute, the product of p minus 1 times q minus 1. Let's just give this a name. The name is phi of n. Okay, I guess I could have more accurately written phi of pq. And, given E, what she can do, she computes the unique element D, because E is coprime to that thing, there should be a unique, did I want to call it phi? Just be consistent with my notes, yeah? So she computes a D satisfying E times D is equivalent to 1 mod, this funny phi of n that we defined here. What in the world is this? Okay, so modulo this thing. So basically she computes the inverse of E mod phi of n. Okay, and that's basically it. Now the question is, what's the public key and what's the private key? Well, she publicly releases the public key, which is, it consists of 2 things. N is public, right? That's the thing that we want to factor. And the public key is E, right? So maybe I'll do this in red. This E was chosen here, right? And she privately stores S, which is equal to, and maybe I don't know why this thing's not switching colors yet. There it goes. Okay. She privately stores n again. I mean, n is public anyway. You don't actually need to store it, of course, in that regard. But she stores that and D, right? And so that's D, and here was D over here, right? D was, in step 3, it was the inverse of E mod this phi of n. Okay, so what is the trick to all this, right? The trick to all this intuitively is that n is public knowledge, but kind of the key to really getting under the hood of the scheme is you don't want n, right? You don't want p times q. You actually want p minus 1 times q minus 1. This is really what you want, right? This phi of n. You want to get your hands on that. Okay? And so given just n, it's not clear how to compute this thing. That's intuitively why this is believed hard. We'll talk about this briefly in a second again. Okay, so that's how she creates the keys. And now let's see how a member of the public encodes a message to Alice. How the public encrypts a message. Oops. Using your public key P. Okay. So suppose Bob wants to encrypt some string, right? So it's a string of 0s and 1s, and that means I could also think of it as an integer, of course. So he wants to encode the string, and the string needs to be at most log of n bits long, and the exercise 44 gets you to think about why that's an upper bound given kind of the parameters I've chosen so far. Okay, and what does he do? He computes. So now let's think of m naught as a string, of course. Just think of it as the integer that string represents. So he computes the ciphertext, or the encrypted text, as follows. So m is the message, so we'll define the ciphertext as e of m. And it's very simple, square multiply, right? Takes the message, raises it to the power e. Remember, e is coming from the public key, right? It's over here. That's e right there. So e is coming from the public key. And then, of course, mod n. Okay, so e and n were parts of the public key, and m is his own personal message. Okay, and then he just sends e of m to Alice. Right? That's how Bob encrypts a message to Alice. Okay, there's nothing to prove there. That's just a fact, right? How Alice decrypts now, given her secret key, there is a bit of a proof required here, which I'm going to skip. And ciphertext e of m. So what does Alice do? She takes e of m, right? So that's what Bob sent to her. That's a some string, right? Or an integer if you like. And she raises that to the power d. Remember, d is her secret key right over here. That's this thing over here. That's part of her secret key. And mod n. And then takes a mod n. And this, the claim is that this will allow her to recover the message m. If you take the encoded thing, you raise it to the power d, again, square and multiply, mod n, you will recover the message perfectly. Again, I'm not going to prove this. It's not too difficult. It takes a couple of lines, but let's not sidetrack from the story here. So the point is that this is how the keys are produced. This is how a message is encrypted, and this is how a message is decrypted. Okay, so the last thing we care about, right? The purpose of this whole lecture is how do we break the scheme? So how factoring breaks RSA. Okay, so let's assume there is an adversary. We've got to give this person an Eve, so we'll call this evil person Eve. Sorry, we've got to give him a name, so we'll call this evil person Eve, right? So let's suppose I have an adversary. Okay, substitute whatever name you want. Can factor. Remember, the public key was n and e. So can factor n equals pq right into the primes p and q. So suppose they're able to do this. They have a quantum computer, say. Okay. So since e is public knowledge, right? That was part of the public key. The public key was both this capital N and this little e. She can recompute the only other missing parameter, which was, e times d was supposed to be equivalent to 1 mod this funny phi of n, right? So she herself can, she can recompute d. Sorry, so that's sitting right here. Okay? Thus obtaining, it's still blue, thus obtaining basically the private key, which is s of d comma n. Okay, so let's quickly scroll up, right? So what happened here is, remember, Alice picked this random element e. That was publicly announced, right? And so was capital N. And so basically, but since Eve knows not just n, but given n, she's able to recover p and q. That means she can compute, this funny phi of n, and she knows e. That means she too can execute line 3, just like Alice did, right? She can compute this unique d, and that means she knows not just the public key, but also the private key. She knows d. And so what that means is that, of course, she can not only decrypt any incoming messages to Alice, but she's actually completely broken the scheme in the sense that she knows all the secret information too, right? It's not that she's just found some backdoor to decrypt messages, right? No, she's really broken the whole thing. Okay? And so that's how you break RSA using factoring. So in a nutshell, remember, the idea is that, what makes, why the thing relies on factoring being hard is just simply because given the product of two primes p and q, it's not clear how to recover the product of p minus 1 times q minus 1. Okay, if you could do that, then you could break RSA essentially. Yeah. So factoring allows us to map pq to p minus 1 q minus 1. That's essentially the link in the chain that needs to be broken. Okay, so that's it. That's the full lecture. So today we talked about Shor's factoring algorithm. We also defined and formalized the factoring problem in terms of its complexity theory. And I think a good closing remark is just to think back to the crossroads. Next time you're bored and you want something to reflect on, and the deepness of life, if you will, right? Think about that crossroads, right? One of these statements must be false, right? So either, well, let me state it slightly differently. Either it's the extended Church-Turing thesis must be false, or we cannot build large-scale quantum computers, or there is a classical factoring algorithm that's efficient, right? One of those three has to be true. And we don't know which one, but one of them has to be true. Okay, good. That's it. Hope you guys have a good week. And as I said, the next assignment should hopefully be released shortly. All right, have a good one, guys.